Hello friends, in previous lecture we have studied about the language of chemistry and the atomic structures. In today's lectures I am going to describe the basic concept of volumetric analysis, normality, molarity, molality, percentage strength, mole fraction, titrations and etc. We will also solve the basic multiple choice questions those were asked in your previous entrance examination. I have also selected some of the important multiple choice questions from the Indian entrance examination book. Let's start now. Before dealing with the titration process, we have to know the basic concept of standard substance. Primary standard substance and secondary standard substance. These are two types of standard substance, and the solution of primary standard substance is known as primary standard solutions. Substances whose standard solution could be prepared directly by weight are known as primary standard substance, and their solutions are known as primary standard solutions. By weighing the required amount, we could easily prepare the solution of primary standard substance. For example, oxalic acid, sodium carbonate, potassium dichromate, silver nitrate, Mohr salt, these are known as primary standard substance, and their solutions are known as primary standard solutions. And here are different criteria for the substance to be primary standard substance: non-toxic, non-hygroscopic, non-deliquescent, and it should be available in pure form. It should be invariant in composition, either in solid or solution state. In both solid and solution state, the substance should have invariant in compositions. The composition of substance should not be changed in solid and solution state. And the substance should have high equivalent and molecular weight. These are the criteria for the substance to be a primary standard substance. And secondary standard substance. Secondary standard substance are such type of the substance whose standard solutions could not be prepared by directly weighing, but they are prepared by titrating with primary standard solution. With the help of primary standard solutions, the concentration of secondary standard solution is quantified. To calculate the concentration or strength of secondary standard solution, we have to depend upon the primary standard solutions. Only then we could easily calculate the secondary standard substance or secondary standard solution concentration. Sodium hydroxide, HCl, sulfuric acid, nitric acid, and potassium permanganate are the example of secondary standard substance, and their solutions are known as secondary standard solutions. Remember, the strength of such type of the solutions could be calculated by using primary standard solutions. Titration. What is titration? Titration is the process to determine the strength of unknown solution with the help of standard solutions. With the help of primary standard solution, we could determine the strength of unknown solution. Strength means concentration. So this process is known as titration. For the titration process, we have to use two types of instrument. One is known as burette. This one is known as burette, and this is known as conical flask. And the substance or the solution which is placed inside the burette is known as titrant, Titrant, and the solution which is kept in the conical flask is known as titrant, Titrand, or it is also known as titrate, Titrate. So this is the general instrumentation of titration process. This one is burette and this one is conical flask, and the solution kept inside the burette is known as titrant, and the solution kept inside the conical flask is known as titrant. And the unknown solution means such type of the solution whose strength is not known, and it is generally placed in conical flask. And the solution whose concentration is known, that is known as standard solution, is kept in burette. So it is not the obligate case. We could also change the preparations of such type of the solutions either in the burette or conical flask. So it is not an obligate. We could also place the unknown solution in burette or in conical flask. Indicator. Thought substance added to the conical flask to determine the completion of reaction by changing color. We have to know the completion of reaction. To know the completion of reaction, we have to place or we have to kept a thought substance except titrant and titrant inside the conical flask, that is known as indicators. An indicator changes the color when the reaction is completed. So after the completion of reaction, the color of the indicator gets changed so that we know the completion of a reaction. Equivalence point. The point at which the equivalent quantity of titrant is added to the titrant is known as equivalence point. It is simple, right? The equivalent quantity of titrant is added to titrant is known as equivalence point. Here is titrant and here is titrant, and it is known as theoretical endpoint. The endpoint is the completion of reaction which is detected by changing the color of indicator, right? The completion of reaction which is detected by changing the color of indicator, right? During the endpoint or at the time of endpoint, the color of the indicator gets changed. So we will also study about the type of indicators. So the indicator is such type of the substance which color change after the completion of reaction. So after the completion of reaction, endpoint is obtained and the completion of reaction is detected by changing the color of the indicator. And titration error is the difference between the endpoint and the equivalence point. Endpoint and equivalence point will not be same. Equivalence point and endpoint may not be same, and there is some difference between the equivalence point and the endpoint, and this difference is known as titration error. It is mainly due to the indicator process. Indicator use or requires sometimes some of the time is required by the indicator to change the color after the exact amount of titrant is added to the titrant. So endpoint is obtained only after the equivalence point because indicator takes some times to change the color. However, the equivalence point is already obtained. Types of titration. There are 4 different types of titration: acid-base titration, redox titration, precipitation titration, and the complexometric titration. We will study one by one. First one is acid-base titration. It is also known as neutralization titration. In acid-base titration, the concentration of either acid or base solution is found by calculating the equivalence point of reaction with the help of sharp change in color of an indicator, right? And in acid-base titrations, either phenolphthalein or methyl-orange are most commonly used indicators. So in this type of the titration, we have to calculate the strength of either acid or base. Acidimetry. In acidimetry, the strength of acid solution is determined by titrating it with standard base solution. In acidimetry, the standard substance or standard solution is base, and we have to calculate the strength of unknown acid solutions. That is, the strength of acid solution is unknown and we have to determine it by using the standard base solution. In alkalimetry, we have to determine the strength of alkali solution, means basic solution, by titrating it with standard acid solution. In alkalimetry, acid is standard and base is unknown. We have to calculate the strength of basic solution. Here is concentration factors. It is also known as normality factors. So it is the ratio of the weight taken divided by weight to be taken. So weight taken divided by weight to be taken. Weight to be taken is also known as theoretical weight. So weight taken divided by weight to be taken is known as concentration factor or normality factor. It is simply ratio. Selection of indicator. this topic is very important. Indicators should change the distinct color near the equivalence point of the titrations. So only we know the completion of reaction after the change in color of indicators. If indicator does not change in the color near the equivalence point, then we do not know the end point of the titration, or we do not know whether the reaction is completed or not. So in this case, we have to select source type of the indicator which change the sharp change in color at the time of equivalent point of the titrations. Phenolphthalein pH range 8.2 to 10 and the methyl orange 3.1 to 4.4. So we have to focus only upon phenolphthalein and the methyl orange. So indicators are either weak organic acid or weak organic base. So phenolphthalein is weak organic acid and methyl orange is the weak organic base. So pH range of phenolphthalein is 8.2 to 10 and methyl orange 3.1 to 4.4. So it has pH range in basic medium, so it has pH range in acidic medium. The color of phenolphthalein in acidic medium is colorless, means it has no any color. However, in basic medium it has pink color. Similarly, the color of methyl orange in acidic medium is red and in basic medium it is orange. So while the process of titrations, if strong base and strong acid are used, then we could select either phenolphthalein or methyl orange as indicator. In case of strong acid and weak acid, phenolphthalein is used as the indicator. Weak base and the strong acid, methyl orange should be selected as the indicator. And in case of weak base and weak acid, no sharp change in color at the equivalence point, so no any indicators are available. In some cases, phenol red is used as the indicators. So 4 to 10 pH and 6.5 to 10 here. So this 4 to 10 means at the pH range of 4 to 10, a sharp steep line is obtained in the titration curve. I will explain about the titration curve. This curve is known as titration curve, right? And this curve is related to the selection of indicator, and in y-axis pH of the solution kept inside the conical flask, and in x-axis the base which is kept in the burette. So pH versus strength of base is known as titration curve, right? So in case of strong acid and strong base, here HCl is a strong acid, right? In case of strong acid and strong base, initially the pH of the solution kept in the conical flask is very low, right? Nearly 1. Right? HCl is kept inside the conical flask, and from the burette drops and drops of the bases are added continuously. And in initial process of the titrations, the pH of the HCl solutions kept inside the conical flask is very low. After the more and more drops of sodium hydroxide or the strong bases, in any type of the strong bases, sodium hydroxide is one of the important strong base, and from the burette drops and drops of the bases are added in the conical flask. Then due to the presence of OH minus in the conical flask, the pH of the HCl solution now gets increased in linear fashion like that. And after the equivalence point or near the equivalence point, there is a steep rise in the pH of the solution kept inside the conical flask. So this steep rise in pH is known as equivalence point. So it marks the equivalence point. So after the equivalence point, there are no free H plus ion present in the conical flask. Then only OH minus is present, because more and more drops of the OH minus is added from the burette. Then due to presence of OH minus, there will be increase in the pH, right? So this is known as strong base and this is known as strong acid. So this one is the curve for the strong acid and strong base. So this line shows the equivalence point, steep rise in pH. So in these regions there will be sharp change in color. So the detections of sharp change in color by the indicator is governed by this steep rise in pH. Due to the absence of H plus ion and presence of only OH minus ions, after the equivalence point, the line becomes straight toward the x-axis. So that the steep rise in pH marks the equivalence point, and HCl has equivalence point near 7, right? So HCl is a strong acid, and the equivalence point of the titrations between strong acid and strong base lies near 7. It is equal to 7. The pH will be in 7, and the range of the pH will be 4 to 10, right? This 4 and this is about 10. So we have to select source type of the indicator which has pH range between 4 and 10. It means either methyl orange or phenolphthalein could be easily used, right? The methyl range has pH 3.1 to 4.4, and the phenolphthalein has the pH range 8.2 to 10. Then these both lie between 4 and 10. So phenolphthalein and methyl orange, either of these type of the indicator could be used in strong acid and strong base titration. In the case of weak acid and strong base titrations, this one is weak acid. It is the representation of acetic acid, and acetic acid is an organic acid, and organic acids are general weak acid. And in initial process of the titrations, acetic acid has some higher value of pH than that of the hydrochloric acid because it is weak acid. It could not furnish as much as H plus ion which are furnished by the HCl because it is weak acid, so that the pH of the acetic acid is higher than that of the HCl. Then by the additions of the OH minus ion from the burette or the base from the burette, the pH slightly increased, and in these regions steep rise in pH occurs, right? So after the completion of the equivalence point, here is only base present in the conical flask, so the pH of that solutions will become constant. So it is the pH range of strong base which is added from the burette in case of weak acid and strong base titration, right? So this is the range, right? So this is above the 7, then we have to select source type of the indicator which has pH range 7 to 10, right? So in case of 7 to 10, what is the pH range of phenolphthalein? 8.2 to 10. So phenolphthalein could be easily used in case of titration between weak acid and the strong base because the equivalence point lies in the regions between 7 and 10 in case of weak acid and strong base. So in the process of titration of weak acid and strong base, we could easily use phenolphthalein as an indicator. And in case of strong acid and weak base, so let us know about this. So this is the pH range, or this is the pH range of strong base, right? This is the pH range of strong base. In case of strong acid and weak base, strong acid means HCl, and we have to know the weak base. For example, ammonium hydroxide, right? Ammonium hydroxide is a weak base. So in case of the titration between strong acid and weak base, initially the pH of the solution kept inside the conical flask is like the HCl solutions, right? Is this, right? Then after the equivalence point, right? The equivalence point, the pH of the solution present inside the conical flask starts to increase. However, it does not increase as much like that of the strong base because we have kept inside the burette a weak base. So weak base furnishes lesser amount of OH minus ion as compared to that of strong base. Then the pH range will be in this region, right? This region, right? This region. So this will be the pH range of the weak base inside the conical flask after the equivalence point, and this lies between this point and this point, right? So what is the pH range in this? So 4 to 7 point something, or 4 to 8, right? So in 4 to 8 pH, there is what type of indicator available? So in case of 4 to 8, so phenolphthalein is not used in case of the pH range between 4 to 8 because phenolphthalein is used only after the pH 8 to 10. the pH range of the phenolphthalein is between 8 and 10. So phenolphthalein could not be used in this case because the equivalence point or the sharp steep rise occurs in the pH range between 4 and 8. So we have to use methyl orange because methyl orange has the pH range 3.1 to 4.4 and it falls between these regions. So methyl orange is used in the titration between strong acid and weak base. Similarly, in case of weak acid and weak base, this is the graph, right? This one is graph. So in these regions there is no any steep rise in the pH. There is some steep rise in pH, but in this region there is no indicator available. So we could not use any type of the indicator in case of the titration between weak acid and weak base. In sometimes phenol rate might be used, but it is not usual case. So in case of weak acid and weak base titration, no any indicator are used due to the absence of sharp change in color near the equivalence point. So these all processes are the selection of indicators in titration curve. Redox titrations. This is another type of the titrations. It is based upon the oxidation and reduction concept. The equivalence point is determined by sharp change in oxidant and reductant, which finally change the potential of the system. This is determined by using Nernst equation, right? We have to know the Nernst equation to calculate the potential of the systems. So this is the ratio of the oxidant and reductant. And here are different examples of redox indicators. Internal indicators, methylene blue and safranin. Self indicator, potassium permanganate act as the self indicator. We have to know this. This is very important. So in case of the titrations between potassium permanganate and the oxalic acid or Mohr salts, we could not use any type of the indicators because potassium permanganate itself act as the self indicator because it is in pink color. And the external indicator is potassium ferricyanide. So here is the reaction between Mohr salts and the potassium permanganate. This is an important example of the redox titrations. Right? This is Mohr salts and here is potassium permanganate. During the titrations, potassium permanganate changes to MnSO4, that is, it is reduced, and the Mohr salts change to Fe2SO4 whole 3, that is ferric sulfate. The Mohr salts change from Fe2 plus to Fe3 plus, and the KMnO4 change from Mn plus 7, that is the oxidation number of manganese in KMnO4 is plus 7 to Mn plus 2. So iodometric titration is another type of redox titration. It is also an example of redox titrations. And in case of iodometric titrations, the standard solution used is hypo solution, Na2H2O3.5H2. It is known as hypo solution. And iodine, which is liberated from the potassium iodide by means of chemical reaction, is titrated against the hypo solutions. So iodine is liberated either from the potassium iodide or any other type of the compound or element whose strength is going to be determined. So from such type of the element or compound, iodine is liberated. This I2 is liberated, and this liberated I2 is treated against the standard hypo solutions. And here is the reaction between the titrations of a standard hypo and the iodine. So it is known as iodometric titrations, and the indicator used is stars, and the color of the stars will be changed due to the presence of I2 solutions, right? The color of the stars will be blue if there is presence of I2. And to give ions should be in highest possible oxidation state, right? It is very important point, right? To give iodometric titrations by any ion, it should be in highest possible oxidation state. We will discuss this concept in tackling the numerical problems, right? While we solve the multiple choice questions, we will tackle about this concept. Another is iodometric titration. Remember, iodometric titrations. It is not iodometric, it is iodometric. Here is IA. In case of iodometric titrations, standardization of solution is governed by titrating it with the given standard ionic solutions. So iodine is taken in the form of standard iodine solution, not in the form of the potassium iodide it is taken in the form of standard iodine solution, right? Iodometric titration. Another type of titration is precipitation titration. It involves the precipitation reactions, right? Here is a precipitation reaction between silver nitrate and sodium chloride. Silver chloride is precipitated out and sodium nitrate is also obtained. So in case of precipitation titrations, Moore's method, Bollard method, and adsorption indicators, there are three types of the indicators used in the precipitation titration. Potassium chromate is used in Moore's method, and ferric nitrate is used in the case of the Bollard's method, and adsorption indicator fluorescent dye is used in case of the adsorption indicators, right? It is very simple. And in case of complexometric titration, metal ion in the solution are determined by using complexometric titration. It is used in the case of determination of hardness of water, right? Complexometric titration. And ligand, here is one ligand concept, right? Based on the coordination chemistry. So ligand, complexing agent means ligand, right? In this case, EDTA is written, ethylene diamine tetraacetic acid. EDTA is one type of the hexadentate ligand, and this hexadentate ligand or EDTA is titrated with the metal ion to get metal ion and EDTA complex, right? Metal ion and EDTA complex. In this case, in complexometric titration, indicators are also used. And the indicator in complexometric titrations are also the complexing agent, right? Also the ligand. Indicators are also ligand. So these are the different types of titrations. Acid-base titration is very important. However, another redox titration, precipitation titration, and complexometric titrations are not so important for you in the point of examination. First, concentration. What is concentration? Concentration of a solution refers to the relative amount of the solute and the solvent present in a solution. So concentration is nothing. It is the general expression of the amount of solute or amount of solvent. In general, amount of solute refers to the concentration. And percentage method is one of the important type of methods for the expression of the concentrations. Percentage W by W, W by V, B by V, and B by W. Here are different formulas for the calculation of percentage compositions. So you have to remember this formula to solve any type of the numerical questions. Normality. Normality is the number of gram equivalent of solute present in a liter of solutions. It means how much number of gram equivalent of solute is present in a liter of solution, which denote the normality. 1 liter of solution contains how much number of gram equivalent of solute. That is known as normality. And normality includes the volume. Here is volume, right? Here is the general formula for the calculation of normality, volume of solution in liters. So due to the involvement of volume during the calculation of normality, the normality changes with temperatures. In general, normality decreases with increase in temperature, right? Normality decreases with increase in temperatures. And here are different formula for the calculation of normality. Number of gram equivalent. Number of gram equivalent is calculated by using this formula. Mass of substance in gram divided by equivalent weight. And we have already discussed about the calculation of equivalent weight. And normality is number of gram equivalent of solute divided by volume of solution in liter. Similarly, here are different methods for the calculation of normality. You have to remember this formula to solve the numerical problems in any case. Basics for the normality equation, right? What are the basics for the normality equations? This is known as normality equations. N1b1 is equal to N2b2. If volume is kept in liters, then N1b1 is equal to the number of gram equivalent of acid or either base, and N2b2 is known as number of gram equivalent of either acid or base, right? This B is the volume in liter, right? Volume should be present in liter to get the number of gram equivalent. So number of gram equivalent of one substance is equal to the number of gram equivalent of another substance in any type of the neutralization reactions. Number of gram equivalent of one substance is equal to number of gram equivalent of another substance when these both substances are reacting together. So in that conditions, N1V1 is equal to N2V2. So normality of the mixture, either acid mixture or either base mixture, is calculated by this formula: N1V1 plus N2V2 divided by V1 plus V2. N1 is the normality of one type of acid and N2 is the normality of another type of acid. In case of base, N1 is the normality of one type of base and N2 be the normality of another type of base. In case of normality of the acid and base mixture, right, acid base mixtures, then N1 be the normality of either acid or base and N2 be the normality of either acid or base. If N1 is the normality of acid, then N2 be the normality of base, and a negative sign should be written here. Here is positive signs, here is negative signs. This negative sign refers to the neutralization process, right? Neutralization. Due to neutralization, negative sign is written because acid and base gets neutralized. Acid and base are neutralized in acid-base mixtures. If W gram of an acid is completely neutralized by V ml of the base of normality, then here is the formula: weight in gram of acid by gram equivalent weight of acid is equal to normality of base into volume of ml divided by 1000. You have to remember this formula. This formula also. When Va ml of acid of normality Na is mixed with Bb ml of base of normality Nb, then if number of gram equivalent of acid is equal to the number of gram equivalent of base, then the solution will be neutral. And if number of gram equivalent of acid is greater than that of number of gram equivalent of base, then the solution will be acidic. And if number of gram equivalent of acid is less than that of number of gram equivalent of base, then solution is basic, right? This is very important, right? This is very important concept. These all points are very important. Normal solutions means if simply n is written, then it will be normal solution. N by 2 semi-normal solution. You have to remember this, right? Molarity, right? The number of moles of solute present in a liter of solutions. 1 liter of solution contains how much number of moles of solute, which denotes the molarity. And molarity also involves the volume, so it decreases with increase in temperatures. Most common way of representing the concentration of solution, that is molarity. And when solute is diluted by x times, then molarity also decreases by x times. We will discuss this type of the topic later on. Number of moles is calculated by using this formula. We have already discussed in the chapter mole concept about this formula. Here are different methods for the calculation of molarity. Number of moles of solute divided by volume of solution in liters. These are different types of the formula. You have to remember this formula to tackle the numerical problems in any case. The relationship between normality and molarity, right? Normality into equivalent weight is equal to molarity into molecular weight. Next one, formality. For ionic compound, gram formula weight is written in place of molecular weight since they have no discrete molecules. Ionic compounds have no any discrete molecules. Ionic compound have no molecular formula. So in case of ionic compound, formality is written in place of molarity. However, the normality and formality are different things, but formality and molarity are the same things. A number of formula weight in a gram dissolved per liter of solution is known as formality. Molality. Number of moles of solute present in 1 kg of solvent, right? 1 kg of solvent. Remember, this is in solvent. This is solvent, not solution. It does not change with temperature because it does not involve any volume, and it is most inconvenient method. Molar solutions are less concentrated than the molar solutions. Remember this, and unit will be mole per kg. Here are different methods for the calculation of molality. Molality is equal to number of moles of solute divided by weight of solvent in kg. Remember, weight of solvent, and it should be in kg. And here are another formula. You have to remember this to tackle the numerical problem. Next one, ppm or ppb. ppm means parts per million and ppb means parts per billion. Here are different formulas for the calculation of either ppm or ppb. Weight of solute by weight of solution into 10 to the power 6 ppm, and weight of solute by weight of solution into 10 to the power 9. We have to remember this formula. Mole fractions, ratio of number of moles of one component, either solute or solvent, to the total number of moles of the solution. So this gives the mole fractions. It is ratio, right? Mole fraction of solute is equal to the number of moles of solute divided by number of moles of solute plus number of moles of solvent. Mole fraction of solvent, number of moles of solvent divided by number of moles of solute plus number of moles of solvent. So the sum of the mole fraction of solute and the solvent is always equal to 1. You have to remember these relationships and you have to remember this type of the formula. These are very important to tackle the multiple choice questions. Relationship between mole fraction of solute and the molality, right? This formula is true only for the aqueous solutions. Here 55.5 refers to water, pure water, and x1 is the mole fraction of solute and m is the molality. A demol unit, 1 demol unit represents 1 mole of solute present in 1 liter of the solution at 0 degrees Celsius. It is simply a definition. An indicator used in titrations, I have already discussed about this. In case of strong acid and strong base, either phenolphthalein or methyl orange is used. In case of strong acid and weak base, methyl orange is used. In case of weak acid and strong base, phenolphthalein is used. And in case of weak acid and weak base, no any indicators are available. In some cases, phenol red is also used. In this way, the theoretical part of this chapter have been finished now, and we will start the multiple choice questions. Let's start now. Multiple choice questions. Now let's start some multiple choice questions. Those were asked in your previous entrance examinations. This one is part 1. We will deal about 50 questions here, and in another part, another 50 questions will be solved. The number of millimoles of HCl required to neutralize 10 ml of 0.2 m sodium carbonate is, this question was asked in MOE model questions. We have already discussed number of gram equivalent of acid is equal to number of gram equivalent of base for the complete neutralizations, right? Then I have already discussed about this formula, right? You have to remember this formula. Weight in gram of acid by equivalent weight is equal to normality of base time into volume in milliliter by 1000. Just put the value. Weight in gram of acid divided by 36.5. 36.5 is the equivalent weight of HCl. Here is HCl. What is the equivalent weight of HCl? 36.5. Molecular weight by basicity, and molecular weight is 36.5. Basicity is 1 because here is only one hydrogen is present. So 36.5 is equal to 0.4 into 10 by 1000. Where is 0.4? Here is 0.2, right? 0.2 molarity means 0.4 normality. We have to put normality here, right? How? 0.2 molarity is equal to 0.4 normality. Here is one relationship between normality and the molar. The molecular weight of sodium carbonate is 106, right? 106. And the equivalent weight is 53. How 53 is obtained? 53, right? This 53 is the equivalent weight and 106 is the molecular weight. And if you divide molecular weight by equivalent weight, then 2 is obtained, right? And 2 times the molarity is equal to the normality for sodium carbonate, right? How 53 is obtained? Molecular weight by 2. Why 2? We have already discussed about the calculations of equivalent weight of the salt, that is molecular weight divided total charge. How many number of charges are present? Sodium only one positive charge, then 2 into 1 positive charge means 2. That is either total charge in cation or either total charge in anion. So molecular weight divided by 2. So total charge either positive charge or negative charge, that will be 2. Then 106 divided by 2 is 53. So 53 is the equivalent weight of sodium carbonate. And if we divide the molecular weight by 53, then 2 is obtained, so that the normality is 2 times greater than that the molarity in case of sodium carbonate. That's why 0.4 is obtained here. Into 10, 10 is this, and divided by 1000 is according to the formula. And we have already discussed about the relationship between number of moles and the weight in gram, right? Number of moles is equal to weight in gram divided by molecular weight, right? Divided by molecular weight. Then weight in gram is equal to number of moles times molecular weight. So number of moles of acid times molecular weight of acid divided by 36.5 is equal to, and molecular weight of acid is 36.5. This 36.5 and 36.5 will be cancelled out. the number of moles of acid will be 4 millimole. So answer will be B. Remember, this question is very important. Next question. 100 ml of 0.5 molar H2SO4 and 0.1 liter of 1 molar HCl. The normality of the resulting solution will be. We have to calculate the normality. And here is the formula for the calculation of these numerical questions. So N1 B1 plus N2 B2. N1 is the normality of H2SO4. B1 is the volume of the H2SO4. N2 is the normality of HCl, and B2 is the volume of HCl. Then 100 ml. So we have to put 100 in case of B1. Right? Then what is the normality of H2SO4? 0.5 molarity of H2SO4 is given. Then we have to convert this into normality. We have already discussed about the relationship between normality and molarity. Normality into equivalent weight is equal to molarity into molecular weight. That is, molarity is equal to molecular weight divided by equivalent weight times the molarity. And what is the molecular weight of H2SO4? That is 98. And what is the basicity? That is S2, means 2 number of replaceable hydrogen. So basicity will be 2. 98 divided by 2 will be 49. So 49 is the equivalent weight. And if we divide the molecular weight by equivalent weight, then 2 is obtained. So the normality will be 2 times greater than that of molarity. So 0.5 into 2 will be 1. So 1 is written here. Then this 0.1 liters will be converted into milliliter, that is 100 into 1 molarity. So 1 molarity means 1 normality in case of HCl, because number of replaceable hydrogen is equal to 1. That is, basicity is 1. Molecular weight by 1. So equivalent weight is also equal to molecular weight. So answer will be 1 normal. Answer D. Very important questions. Pollution in atmosphere is measured in, right? It is measured in ppm. You have to remember this. This question was asked in IOM 2018. Right? Next question. Right? Volume of sodium carbonate to neutralize 1 liter of 1 normal H2SO4. I think this question is incomplete, because the question asked about the volume of sodium carbonate, right? And the strength is not given. Then how to calculate this, right? So if strength is given, then normality equation is useful for the calculation of volume of sodium carbonate. However, there is no any strength. So if the question is asked about the amount of sodium carbonate, then we have to solve that question on the basis of these questions. Then answer will be 106 gram. However, this question is incomplete, I think. Next question. Calculate the molarity of pure water. The molecular weight of pure water is equal to 18, right? Then gram molecular weight will be 18 gram. And we have to use the density concept to calculate the molarity of pure water. 1 gram per ml is the density of water. It means 1 ml of water weighs 1 gram. Then here is a formula for the calculation of molarity. Then weight of water in gram is equal to 1 gram according to density concept. 1 gram per ml means 1 ml of water weighs 1 gram. Then weight of water will be 1. Then gram molecular water 18. Then 1000. Here is 1000 according to the formula. Then 1 means 1 ml. Here is 1 ml. So 1 gram of water occupies 1 ml volume. That means 1 ml of water weighs 1 gram. Then 1 by 18 into 1000 by 1. This is 1 ml and this is 1 gram. Then answer will be 55.55 molarity. Then pure water means it is pure. It does not contain any other type of the impurities. Means the density of that water should be 1 gram per ml. So density of that pure water should be 1 gram per ml. So we have to use the concept of density to calculate the numerical problems of this type. This is very important question. 55.55 molar is the answer. Strongest base and the weak acid indicator is, right? The salt formed by the combination of strong base and weak acid will be basic. Remember this, right? The salt will be basic, right? Because the base is strongest. So which one is strongest? Base. So salt will be basic. In case of basic salt or basic medium, phenolphthalein is used as the indicator. In case of acidic medium, methyl orange is used as the indicators. And the phenolphthalein has the pH range 8.2 to 10. It is the basic range of pH, so phenolphthalein is used in case of the basic medium because the salt formed by the strongest base in the weak acid will be basic in nature. And phenolphthalein is a weak organic acid. It is generally represented by HPS, and it is weak organic acid, so it undergo the reversible reaction HPH H plus PS minus. And in acidic medium, the color of the phenolphthalein is colorless, right? It is colorless in acidic medium. However, its color changes to pink in case of basic medium. Now let's start. How does phenolphthalein indicate the basic medium by changing the colors? I am going to explain about this, right? In case of basic medium, OH minus is present, right? OH minus is present. Then this H plus minus combines with OH minus ion to give water, so that the concentration of H plus ions in the right hand side of this reversible reaction will go on decrease. Then according to Lee-Chatelier principles, the directions of that equilibrium shifts from the left to right, that is according to the concentration change from high concentration to low concentration, because the concentrations in this right side will go on decrease due to the formation of water by the combination of H plus and OH minus in basic medium, so the color will be pink, or in case basic medium. In case of acidic medium, H plus will be present, right? What happened in acidic medium? In case of acidic medium, H plus is present, and this H plus is common to this H plus, so the concentration of the ion in the right hand side will go on increase. So due to that, the direction of the equilibrium will be from right to left, so the condition will be colorless and acidic medium. So in case of acidic medium, the color of the phenolphthalein will be colorless, and in case of basic medium, color will be pink. Methyl orange, right? Methyl orange has pH range 3.1 to 4.4, and it is a weak organic base, and it is represented by MUS. Similarly, methyl orange works in case of acidic medium. The color of methylene orange will be red in case of acidic medium. So let's explain about this. In case of acidic medium, H plus will be present in that solutions. So due to presence of H plus, this OH minus and H plus combines to form the water, so that the concentration of OH minus in the right hand side will go on decrease. Then the direction of equilibrium shifts from left to right due to the difference in the concentration, because the concentration of MUOH is high and OH minus is low due to the formation of H plus and OH minus in water, and the color will be redder in acidic medium. In case of basic medium, OH minus will be present, and this OH minus will combine with this OH minus, right? So it does not combine, but here is a common ion effect, that is common ion, so that the concentration of OH minus in the right hand side will go on increase. So due to that concentration differences between the right hand side and the left hand side, the equilibrium shifts from right to left, and the color will be orange or in basic medium. So this is the main mechanisms of working of indicators during titration method. This is very important, right? Remember this. Next question. Acetic acid has molarity 2.05 molar and specific gravity is 1.03 gram per ml. Specific gravity is nothing, it is density. And molality is calculated by using this formula. Molality is equal to number of moles of solute divided by weight of solvent in kg. Remember, this should be solvent and this should be in kg. Then according to this molarity concept, 2.05 m of acetic acid means 2.05 moles of acetic acid in 1 liter of solutions. We have already discussed about the concept of molarity. Then volume of the solution is equal to 1 liter, that is 1000 ml. Then we have to calculate the weight of solvent is equal to weight of solution minus weight of solute. Then density of the solution was given, that is 1.03 gram per ml. So weight of solution will be 1.03 into 1000, right? We know that density is equal to mass by volume. Mass by volume. And mass is equal to density times volume. Where is the volume? 1000 ml, with 1000 ml is the volume of the solution, then 1000 times the density of the solution gives the 1030 gram, that is the weight of that solutions. So we have to subtract weight of the solutions from the weight of the solute. Then weight of the solute is calculated by using molecular weight of acetic acid, that is 60 gram. Then weight of solute is equal to number of moles times the molecular weight. The number of moles is calculated by using formula mass in gram divided by molecular weight, right? Molecular weight. Mass in gram divided by molecular weight. Then mass in gram or the weight is equal to number of moles times molecular weight. So 2.05 mole is the, here is 2.05 moles of acetic acid times 60 is the molecular weight of acetic acid. Then 123 gram is obtained. Then weight of solvent will be weight of solution minus weight of solute, that is 907 gram. Then molality will be number of moles of solute, that is 2.05 divided by weight of solvent in kg is equal to 0.907 kg is equal to 2.26 mole per kg. Answer. So this question could be solved on the basis of this formula, right? This formula is also helpful for the calculation of this problem. This question is very important. When equal volume of 0.1 molar silver nitrate solution and 0.2 molar sodium chloride solution is mixed, the resulting concentration of nitrate ion, remember nitrate ion in the solution is, right? Here is the general reactions of the above problem. Then initial volume of silver nitrate is let be, and the strength of silver nitrate is given 0.1 molar, and initial volume of sodium chloride will be B. This is assumptions, right? This B and this B is just assumptions because volume has not been given, but the question clearly told about the equal volumes, equal volume of silver nitrate and sodium chloride. Then strength of sodium chloride will be 0.2 molar. Here is 0.2 molar. Then we have to calculate the strength of nitrate ion in the mixtures. The volume of the resulting mixtures will be 2B because 1B will be of silver nitrate and 1B will be of sodium chloride. Then the total volume of the mixture will be 2B. Then strength of nitrate ion will be 0.1, right? Remember, nitrate ion will be furnished by silver nitrate only, right? Nitrate ion should be furnished by silver nitrate ion because sodium chloride should not furnish the nitrate ion. In the question clearly mentioned about the calculation of concentration of nitrate ion. So 0.1 times B. B is the volume of silver nitrate divided 2B is the total volume of the mixtures. Then answer will be 0.05 molarity. Right. Very important questions. Next questions. What is the amount of 10 ml of 1 normal dibasic acid? Molecular weight is equal to 200. Right? We have to calculate the amount of dibasic acid, right, by using this formula. Normality is given, but we have to calculate this weight of solute in gram is equal to 1 gram. Right? So equivalent weight will be molecular weight by basicity. Basicity is 2 because the acid is dibasic. Dibasic means basicity 2. So weight will be 1 gram. Simple question. 1 gram HCl and 1 gram NaOH are dissolved together in 1 liter solution of water. Then the resulting solution will be. We have to calculate whether the resulting solution is acidic, alkaline, neutral, or amphoteric, right? First of all, calculate the strength, right? Strength means molarity or normality, but in this case, molarity will be calculated. So strength will be number of moles of solute divided by volume of solution in liters, right? So volume of solution will be 1 liter in both cases. We have to just calculate the number of moles, right? Number of moles of HCl will be 1 by 36.5. This is the weight of HCl and 36.5 is the molecular weight of HCl. So number of moles will be weight in gram divided by molecular weight 1 by 36.5. Then strength of NaOH is calculated in the similar manner 1 by 40. 1 is the weight of NaOH and 40 is the molecular weight of sodium hydroxide. So 1 by 40. Then strength of HCl is greater than that of the strength of NaOH, right? 1 by 36.5 is greater than that of 1 by 40. So the solution will be acidic. Very important question. 18 molar solution of sulfuric acid was diluted to 100 liters. Find the normality of the solutions. So we have to calculate the normality of the solutions. Right? So normality of sulfuric acid will be 18 into 2 by using this formula, right? because molecular weight will be 98 and equivalent weight is 2, then 98 by 2 is equal to 49. Then molecular weight by equivalent weight is equal to 2. So normality will be 2 times greater than that of molarity. So 18 into 2, 36. The initial strength will be 36. Then initial volume will be 1 liter. So let just assumptions. Then final volume is 100 liter because the solution was diluted to 100 liter. Then the final volume will be 100 liter. So by using the normality equations, answer will be 0.36 normality or normal solutions. Very important questions. You have to just remember this formula and we have to convert the molarity of sulfuric acid into normality. Next question, 0.5 normal concentration of 100 ml solution on dilution to give resultant solutions having 0.2 normal. What is the volume of water that should be added to the solutions? The concentrations of that solution is going to be decreased from 0.5 normal to 0.2 normal, right? So the concentration is decreased, so the dilution has been taken place on that solution so that its concentration has been decreased. So for the dilution we have to add water. So how much amount of water should be added? So the question is asked about the amount of water. So initial strength will be 0.5 normal, here is 0.5, and initial volume will be 100 ml, here is 100 ml. Then final volume we have to calculate. Then final strength will be 0.2 m. Then by using the normality equations, answer will be 250 ml. Then 250 ml is the volume of the solution in final case. Then we have to subtract this volume from the initial volume to calculate the amount of water added, that is 150 ml. Very important question. A toothpaste contains 0.2 gram per liter fluoride, then its value in ppm, right? We have to calculate the value of 0.2 gram per liter in ppm. So here is the general formula of ppm, weight of solute in gram divided by volume of solution in ml into 10 to the 6. 200 ppm will be obtained, and weight of fluoride 0.2 gram and 1 liter means 1000 milliliter. Just use this formula to calculate this problem. The normality of solution containing 5 gram of NaOH per liter is, so we have to calculate the normality by using this formula, right? Simply use this formula and put the value, answer will be 0.125, and the equivalent weight of solute, that is sodium hydroxide, will be 40, right? Equivalent weight is equal to molecular weight divided by acidity in case of base, and here is acidity 1 because here is only one OH minus ion replaceables. Next question, molality, right? This question is very important and it is based upon the molality, right? We have to calculate the molality of the solutions by using this formula. 15% W by V solution is known as 15 gram of sulfuric acid dissolved in 100 milliliter of solution. Then the volume of the solution will be 100 milliliters. We have to calculate the weight of solvent in kg, and the density of the solution is given as 1.1 gram per ml. Then weight of solution will be 1.1 into 100. 1.1 is the density and 100 is the volume. So density times volume gives the weight, that is weight of solution will be 100 because m is equal to density into volume, right? So we have to calculate the weight, and weight of solute is 15 gram, here is 15 gram, then weight of solvent will be 95 gram, right? By using this formula, answer will be 1.61 mole per kg. Very important question. Next question, the amount of copper sulfate .5H2O, it is also known as blue vitriol, required for producing 500 cc of 0.5 normal solution is, right? Remember this formula to calculate the amount of blue vitriol, right? Here is weight of solute in gram, this means amount of blue vitriol. So molecular weight of blue vitriol is 63.5 is the atomic weight of copper, 32 is the atomic weight of sulfur, and 16 into 4 plus 18 is the molecular weight of water, 18 into 5, so 249.5. Equivalent weight will be 249.5 divided by 2. Why this is 2? Because the total positive charge present in copper sulfate, that is 2 Cu2 plus, Cu2 plus. In case of sulfate, SO4 2 minus. So total positive charge or total negative charge, right? Molecular weight by either total positive charge or total negative charge gives the equivalent weight. So 124.75. So just put this value in this equation, then answer will be automatically obtained. Right. Next question. When 100 ml of 1 molar H2SO4 is mixed with 20 molar cc of 5 molar NaOH, then the resulting solution is, we have to calculate whether the resulting solution is acidic, alkaline or neutral, right? So volume of H2SO4 given 100 cc. 100 cc means 0.1 liter, and strength of H2SO4 given 1 molar. 1 molar means 2 normal. We have already discussed about this relationship between normality and molarity. Then Na into Va, right? Na into Va gives the number of gram equivalent, that is 0.2 gram equivalent. In similar manner, number of gram equivalent for NaOH will be 0.1 gram. Then we have to compare the number of gram equivalent between these two cases, that is acid and basic case. So number of gram equivalent of acid is greater than that of number of gram equivalent of base, so the mixture will be acidic, right? Just compare the number of gram equivalent by using this formula, right? Na into Va, right? Na and B into Vb. If volume is in ml, then number of gram equivalent is calculated by NaBa divided by 100 cc, that is 100 ml. Next question. The concentration of cane sugar C12H22O11, it is also known as sucrose, which is isotonic solution containing 6 gram of urea. Isotonic means same concentration, right? Same concentration of urea and cane sugar. Isotonic means same concentration. Molecular weight of urea is 60, right? Here is the molecular formula of urea, and by using this molecular formula, molecular weight will be 60. A number of moles of urea will be 6 by 60 because 6 gram of urea is given. Then 6 by 60 is the molecular weight, 0.1 mole. 0.1 mole of urea is present in 1 liter of solution. Let us consider just. Then the concentration of urea will be 0.1 molar because 0.1 mole is present in 1 liter of solution, means 0.1 molar is the concentration. So according to question, cane sugar is also 0.1 molar because cane sugar is isotonic to the urea, so 0.1 molar, and molecular weight will be 342 in case of cane sugar. Then gram per liter strength should be calculated is equal to molarity into molecular weight. We have already discussed about this formula because gram per liter is equal to molarity into molecular weight. Molarity is 0.1 and molecular weight is 342. So answer will be 34.2 gram per liter. Answer A. Important questions, right? Just remember this relationship, right? What is the normality of ammonium hydroxide solution having density 0.6 gram per ml containing 34% by weight of ammonium hydroxide? Just remember this formula to calculate the normality. Normality is equal to weight percent into density into 10 by equivalent weight, and put the value here. 5.82 normality is the answers, and we have to calculate the equivalent weight of ammonium hydroxide. It is 35.1. 35 is the molecular weight of ammonium hydroxide. By using this molecular formula, we could easily calculate the molecular weight of ammonium hydroxide, and 1 is the acidity, that is number of replaceable OH. Here is only one OH, so 35 by 1 is 35. Answer will be 5.82. Just remember this formula. If 4 gram of NaOH is dissolved in water and volume is made up to 250 ml, the concentration in gram per liter will be. We have to calculate the concentration in gram per liter. It is very simple questions. Just convert this 250 ml into liter. So 4 by 250 because 4 gram of NaOH is dissolved in water and volume is made up to 250. Then 4 by 250 into 1000 will give the answer in gram per liter. Very simple. 1 kg of water contains 4 gram of NaOH. The concentration of solution is best expressed as, right, molal. Here is molal because the weight of solvent is given in kg, that is weight is given in kg. So we know the definition of molality, right? Here is the definition of molality: number of moles of solute divided by weight of solvent in kg. This is the definition of molality. And 1 kg of water, 1 kg of solvent is given, so it will be best expressed in molal. The number of moles of NaOH is 4 by 40, right? 4 is the weight of NaOH and 40 is the molecular weight of NaOH, is equal to 0.1. Weight of solvent is given here 1 kg. Then answer will be 0.1 molal. So 0.1 molar. Next question. In the graph, the titration shows between, here is a titration curve between the pH and volume. In y-axis pH is written, and in x-axis volume of the base added from the burette. And this is the end point of the titrations, and this straight line represent the sharp change in pH during the neutralization. So in case of strong acid and strong base, the sharp change in pH falls in the region of 7, because the pH of strong acid and strong base will be 7 in the end point, right? However, strong acid and weak base, the pH will be less than 7. In case of weak acid and strong base, pH will be greater than 7. We have to just notice about the strong. Which one is strong? Acid is strong, so pH will be less than 7. Then which one is strong? Base is strong, then pH will be greater than 7. In case of weak acid and weak base, no any sharp change in pH is found. So no any sharp change in pH. However, there is sharp change in pH, right? There is sharp change in pH in the region of 7, pH 7. So answer will be strong acid and strong base. In case of strong acid and weak base, weak acid and strong base, the graph will be in another type. So I will discuss about this graph, strong acid, weak acid and strong base, in another lecture. That is volumetric analysis part 2. We will discuss about this. Next question. When 50 ml of HCl reacts with 10 gram of calcium carbonate, then normality of the solution is, we have to calculate the normality of the solutions containing calcium carbonate in 50 ml of HCl, right? Molecular weight is 100 gram, right? Very simple. Equivalent weight will be 50, 100 by 2. Why this 2 is obtained? How this 2 is obtained? Then 100 by 2, right? 100 is the molecular weight of calcium carbonate divided by total either positive charge or negative charge. In case of calcium carbonate, total positive charge is 2. So 100 by 2, 50. So this is the calculation of normality for the calcium carbonate. Then answer will be 4 normal, right? Volume of HCl solution in ml will be 50 ml. Just put this value in this equation. Answer will be automatically obtained. You have to just remember this formula. 0.4 gram of sodium hydroxide is added to 10 ml of 1 normal HCl. Then the resulting solution is, we have to calculate the number of gram equivalent in both cases, right? Volume of HCl is 10 cc, that is 0.01 L. Then normality will be 1 normal, that is the normality of HCl, right? Here is not written, but it is the normality of HCl. Then number of gram equivalent of HCl will be 0.01 gram equivalent. Na into Va is the general form for the calculation of normality. The number of gram equivalent of NaOH should be calculated by using this formula. Number of gram equivalent is equal to weight divided by equivalent weight, right? Weight divided by equivalent weight. Weight of NaOH is given 0.4 gram and equivalent weight of NaOH is 40. So answer will be 0.01 gram equivalent. And in case of acid, 0.01 gram equivalent. In case of base, also 0.01 gram equivalent. So the mixture will be neutral, because number of gram equivalent of HCl is equal to number of gram equivalent of NaOH. So mixture is neutral. Next question. 10 ml of 2 molar H2SO4 is mixed with 10 ml of H2O. Then 10 ml of mixture can neutralize how much amount of 2 normal NaOH? We have to calculate the volume of NaOH that can be neutralized by 10 ml of H2SO4 mixtures. Volume of H2SO4 given 10 ml, right? Strength of H2SO4 4 normal, right? Here is 2 molar given, so 2 molar is equal to 4 normal in case of H2SO4. I have already discussed about this. Then total volume of the mixture will be 20 ml. How this 20 is obtained? 10 ml of, sorry, here is 10 ml of water and here is 10 ml of H2SO4. 10 ml of water is added to the 10 ml of H2SO4 having concentration 2 molar. So total volume will be 10 plus 10, that is 20. 10 plus 10, 20. Then strength will be 10 into 4 by 20 divided by 2 normal. Here is 10 into 4 divided by 20. Just use the normality equation. Then volume of the mixture used is equal to 10 ml. Now this 10 ml of the mixtures of concentration having 2 normality, right, can neutralize how much volume of 2 normal NaOH. Then volume of the mixture used is 10 ml. Here is 10 ml. Then strength of NaOH is 2 normal. Here is 2 normal. Then we have to calculate the volume of NaOH by using the normality equation. This 10 is, how this 10 is obtained? This is volume of the mixture used, and this 2 is the strength of the H2SO4 mixture, and this 2 is the strength of NaOH. So answer will be 10 ml. Simple. This question is based upon the calculation of normality of the mixture. So just you have to use this formula. It is very simple question. 10 cc of n by 2 HCl. So strength of HCl 0.5 normal, volume of HCl given 10 ml, strength of HNO3 nitric acid given 0.1 normal, and volume of HNO3 30 cc. Then strength of H2SO4 given 0.2 normal, then volume of H2SO4 60 cc, right? And just use this value in this formula, then answer will be 0.2 normal. It is very simple question, just remember this formula. A sample of Na2CO3.H2O weighing 0.62 gram is added to 100 ml of 0.1 normal H2SO4. Then the resulting solution will be, right? Volume of H2SO4 is 0.1 liter given 100 ml means 0.1 liter, and strength will be 0.1 normal, strength of H2SO4, right? Strength of H2SO4. Then the number of gram equivalent is equal to 0.01 gram equivalent. In case of sodium carbonate H2O, that is number of gram equivalent is equal to weight given 0.62 gram. So 0.62 gram, because number of gram equivalent is calculated by weight divided by equivalent weight, right? This is the general formula for the calculation of number of gram equivalent, and this the 0.62 is the weight. Here is weight is given divided by equivalent weight of Na2CO3.H2O, that is total molecular weight of Na2CO3.H2O, Na2CO3.H2O divided by 2. So answer will be 0.01 gram equivalent, and here is also 0.01 equivalent. Since the number of gram equivalent of Na2CO3.H2O is equal to the number of gram equivalent of H2SO4, so the resulting solution is neutral. Very important. Aqueous solution of ferric chloride is, right? What is the nature of aqueous solution of ferric chloride? Either is it acidic or basic, amphoteric or neutral? We have to know this, right? We know that ferric chloride is formed from the combination of strong acid HCl and weak base ferric hydroxide. So strong acid and weak base, right? So ferric chloride is formed from the strong acid and weak base. We have to just notice upon the strong, which one is strong? Acid is strong, so solution will be acidic. Similarly, strong acid and strong base, then salt will be neutral. If strong base and weak acid, then the salt will be basic, and weak base and strong acid, then salt will be acidic, and weak acid and weak base, then it depends upon the relative strength of acid. It might be acidic, basic or neutral. Just remember this point. These points are very, very important to know the exact answers of this type. You have 2.5 normal and 0.625 normal solution. In which proportion would you mix this solution to get 1 normal of 1 liter solution? You have to just remember this formula, right? Normality of the mixture is equal to N1V1 plus N2V2 divided by V1 plus V2. So let the volume of the first solution be x ml, then the second solution will be 1000 minus x, because the mixture has volume 1 liter. 1 liter means 1000 ml, so 1000 minus x, and the value of x is 200 ml, right? 200 ml, then another will be 1000 minus 200, that will be 800. So answer will be A. Next question. 1 molar solution of phosphoric acid is, we have to convert the 1 molar solution of phosphoric acid into normality, right? This is the general representation for the relationship between molarity and the normality. Molecular weight will be 98, right? You have to calculate this, and equivalent weight will be 98 by 3, then the normality will be 3 normal. Answer will be C. So just remember how these 3 is obtained. So I am going to explain this, right? In case of phosphoric acid, this is the general structures, right? In some cases, double bond is also written between phosphorus and oxygen here. So we have to know about the basicity to calculate the equivalent weight of any acid, right? Basicity is the number of replaceable hydrogen atom. How many number of hydrogen atom are present here? 3 hydrogen atoms. So these 3 are replaceable, so basicity will be 3. Then the equivalent weight will be molecular weight by 3, because 3 is the basicity. 3 is the basicity. Number of replaceable hydrogen atom will be 3 here, right? 3. So 98 by 3 is equal to equivalent weight of that phosphoric acid, and normality will be 3 normal. So in case of H3PO4 equivalent weight is equal to molecular weight by 3. Now let's come to the other point. In case of H3PO3, phosphorus acid, right? In case of phosphorus acid, only 3 oxygen are present. So 1 oxygen is missing in case of phosphoric acid. Then this oxygen is not in the structures of phosphorus acid. Then this hydrogen is directly bonded to the phosphorus, and the hydrogen which is directly bonded to the phosphorus is not replaceable. Remember this point. Hydrogen which is not directly bonded to the phosphorus is not replaceable. So in case of H3PO3, number of replaceable hydrogen are only 2, this one and this one. This hydrogen is not replaceable because this hydrogen is directly combined to the phosphorus. Only such type of the hydrogen is replaceable which is combined with the highly electronegative element. Oxygen is very electronegative element. So very electronegative element means oxygen. Phosphorus is less electronegative element. So only these two hydrogens are replaceable. So in case of phosphorus acid, equivalent weight is equal to molecular weight by 2 because the basicity will be only 2. In case of hypophosphorus acid, H3PO2, then these two hydrogen are directly combined with the or directly bonded to the phosphorus. Then these two are not replaceable. Then only one is replaceable which combines with the oxygen. So answer will be molecular weight by 1 because 1 is the basicity since only one hydrogen is replaceable. These points are very important, right? Next question. How much water should be mixed with 10 ml of 10 normal HCl to make it exactly decinormal, right? Decinormal means n by 10, that is 0.1 normal. Then strength of HCl given is 10 normal, here is 10 normal, and 10 ml is the volume of HCl, here is 10 ml volume. Then final volume of that whole solution will be 1000 ml. Then we have to subtract this 1000 from the initial volume of the HCl solution to account or to calculate the amount of water added, that is 990 ml, right? Very simple question. Number of moles of sodium in 4.5 liter of 1.5 molar in a solution is, just use the concept of molarity, number of moles of solute divided by volume of solution in liter, that is number of moles of solute will be molarity times volume of solution in liters. So volume of solution in liter will be 4.5 and molarity is 1.5, 6.75 mole. Simple question. 50 ml of 0.2 normal HCl is titrated against 0.1 and NaOH after adding 50 ml of NaOH, which is titrated first. Remaining titration was performed by using 0.5 normal KOH, then the volume of the KOH after titration. So in this case, hydrochloric acid is titrated with two bases, one is NaOH and another is KOH. First of all, titrated with NaOH 0.1 and NaOH, and 50 ml of NaOH is only used in first case. In second case, the remaining HCl solution is titrated with 0.5 normal KOH. Now, in first case, strength of HCl given, right? Strength of NaOH also given, and the volume of NaOH. Then volume of HCl consumed by NaOH in first case will be 25 ml by using the normality equation. Very simple questions. Then N2 into B2 by N1, right? 0.1 is the N2 and 50 is the B2 divided by N1 is equal to 0.2. So answer will be 25 ml. So sodium hydroxide consumes only 25 ml of 0.2 normal HCl. Then the remaining, what is the remaining volume of HCl? 25 ml. So for the remaining volume, that is 25 ml, 0.5 normal KOH is used. So strength of KOH is 0.5 normal, then volume of KOH will be 0.2 into 25 by 0.5 is equal to 10 ml. How this 0.2? The 0.2 is the KOH strength of HCl, and this 25 is the remaining volume of HCl, and 0.5 is the strength of KOH. The answer will be 10 ml. So volume of KOH after titration, or volume of KOH that is used for the titration or for the final consumptions of the HCl is equal to 10 ml. A pressure vessel contains a gaseous mixture made up of 2.34 kg silane and 55.4 kg argon. Then we have to calculate the mole fraction of silane, right? Silane means SiH4, right? SiH4 is this molecular formula of silane. Then its molecular weight will be 32. The molecular weight of silicon is 28 plus 4, 32. The number of moles will be By using this formula, number of moles is calculated. Remember, this value should be in gram. 2340. Here is in kg. 2.34 into 1000. 2340. Answer will be 73.125. And 55400138.5. Then the formula of mole fraction of sealant is equal to number of moles of sealant divided by number of moles of sealant plus number of moles of argon. So answer will be 0.0502. Answer is A. Very simple question. Next question. 0.02 moles of aluminium is reacted with oxygen, whose product is reacted with 2 mole per liter of HCl. What is the volume of HCl will completely reacts with it? And here is the chemical reactions for the first statement. Aluminium plus oxygen Al2O3 means alumina is obtained. According to these reactions, 4 moles of aluminium gives 2 moles of Al2O3. Here is 4. So 4 moles of aluminium gives 2 moles of Al2O3. Then 0.02 moles of aluminium gives 0.01 mole of Al2O3. So after the reactions of aluminium and oxygen, 0.01 mole of Al2O3 is obtained, and which will finally reacts with hydrochloric acid to produce AlCl3 and water. So according to these reactions, 1 mole of Al2O3 requires 6 moles of HCl for complete reaction. Then 0.01 mole requires 0.06 moles of HCl. Then 0.06 moles of HCl means 0.03 liter. This is the formula for the molarity. Molarity of HCl is equal to number of moles of HCl divided by volume in liter. Answer will be 30 cc. This question could also be solved on the basis of equivalent concept. Next question. 10 ml of 2.5 normal NaOH is mixed with 20 ml of 1.5 NaHCl. The mixture is diluted to 100 ml, right? We have to know the nature of the mixture, right? To know the nature of the mixtures, first of all, use these 4 values, right? Volume of NaOH and strength of NaOH. Just multiply these 2 values. Answer will be 25, right? 25. And here is 30. So which one is greater? 30 is greater. So solution will be acidic in nature. Then strength will be calculated by using this formula, right? 20 into 1.5 minus 10 into 2.5. So this negative sign is written here due to the different nature of acid and base, right? One is acid and another is base. There is neutralizations. So neutralization program should be taken place if we add acid into base. So answer will be 0.05 normal, and negative sign should be written here in case of neutralization reactions. Next question. What concentration of sodium chloride finally results from the mixture of 200 liter of 4m NaCl with 300 liter of 1.5 molar NaCl plus sufficient water to dilute the solution to 1000 liter? So final volume of the solution is 1000 liters, that is 1000 is here. Then just use the concept of normality of the mixtures. Then answer will be 1.25 molarity. Here are different data. So very simple questions. Which of the salts produce an alkaline solution when dissolved in waters? So I have already discussed about this, right? So to produce the alkaline solution or the basic solution, the salts should be combined from the strong base and weak acid. So NH4Cl is combined from HCl and NH4H. So HCl is strong acid, so the solution will be acidic. In case of NaNO3, it is formed from the NaOH and HNO3. So both are strong acid and strong base. So in case of that, the solution of sodium nitrate will be neutral. In case of sodium bicarbonate, it is formed from the combination of sodium hydroxide and the bicarbonic acid. Sodium hydroxide is strong base, however bicarbonic acid is weak acid. So answer will be C, because the solutions of the salt formed by the combinations of strong acid and weak base will be acidic, and strong base and weak acid will be basic in nature. We have to just focus on the strong. Which one is strong? The solution will be on that type. A solution of NaOH contains 0.25 moles per dm3, right? dm3 means liter, just liter. Using phenolphthalein indicator titration of 25 cm3 of the solution required 22.5 cm3 of HCl solution for complete neutralization. Then calculate the moles of HCl neutralized. Very simple question. Strength of NaOH is 0.25 mole. 1 DMQ means 1 liter, then 0.25 moles per liter means 0.25 molar. Then volume of NA is 25 ml, 25 CMQ means 25 ml, and 22.5 CMQ means 25 ml. Then by using the normality equation, 0.25 into 25, 0.25 is N1 and 25 means B1 and 22.5 is P2. So answer will be 0.278 moles per DMQ. DMQ means liter. Simple. The normality of 10% NaOH solution is, we have to calculate the normality of 10% NaOH solutions, right? 10% NaOH means 10 gram of NaOH dissolves in 100 ml of solution. Then weight of solute to 10 gram, volume 100 ml. Then just use this formula to calculate the normality. The indicator is chosen in titration of strong acid and weak base on the basis of, right? We will discuss this type of the question in next part, that is volumetric analysis part 2. So the answer will be dissociation constants. I will explain this about the dissociation constant in next lectures. Volumetric analysis part 2. Next question. 4.5 mole of ethane contents, right? Ethane. What is the molecular formula of ethane? C2H2, right? C2H2 is the molecular formula of ethane. What is the molecular weight? 26. 12 into 2 plus 2. Then 26 gram of ethane contains 2 gram of hydrogens, right? According to this molecular formula. Then 1 mole of ethane means 26 gram of ethane. According to the mole concept, contain 2 gram of hydrogen. Then 4.5 moles contain 9 gram of hydrogen. Simple question. 20 ml of 1 NaCl reacted with 30 ml of 0.5 NaOH, the normality of the resulting solution. We have to calculate the normality of resulting solution. Remember, one is acid and another is base, right? So here is the calculation of strength of mixtures. We have to put the negative signs because here is one acid and another base. So neutralization takes place. So we have to use the negative sign there. Then 20 into 1 minus 30 into 0.5. Answer will be 0.1 normal. So in which cases 0.1 normal should be written either in the HCl or NaOH? Just use the concept of gram equivalent. N1B1 is equal to 30 into 5, 15 in case of NaOH, and in case of HCl 20. So which one is greater? NaOH is greater. So answer will be, sorry, in NaOH is not greater, HCl is greater, right? So HCl is greater means here. So answer will be 0.1 HCl. So resulting solution will be acidic in nature because gram equivalent of HCl is greater than that of the gram equivalent of NaOH by using this formula. Right? Next question. This question is based upon the half neutralization concept. Half neutralization. It is based upon the half neutralization. It is very important question and is what asked in MOE 2065. 200 ml of 0.2 molar HCl is neutralized with 0.1 normal NaOH. Then during their half neutralization, what will be the molarity of HCl? We have to calculate the molarity of HCl during the half neutralization. Here is the beaker. Inside the beaker, hydrochloric acid is kept, right? Hydrochloric acid, a volume 200 ml, right? Volume 200 ml and strength 0.2 molar. So in these beakers, sodium hydroxide of concentration 0.1 is added. Now let's come to the point. So for the complete neutralization, what is the volume of sodium hydroxide required? That is 400 ml. This is strength of NaOH, and this is the volume of HCl. This is strength of HCl 0.2 normal. In case of HCl, the normality is equal to molarity because basicity of HCl is 1. Then the volume of NaOH required is equal to 400 ml according to the normality equation. So for complete neutralization, 400 ml of 0.1 normal NaOH is required. However, for half neutralization, the question is asked about the half neutralization. Then in case of half neutralization, only 200 ml of NaOH is added inside this beaker containing 0.2 molar HCl of 200 ml volume, right? This beaker contains 200 ml of HCl having 0.2 molar concentration, and during the half neutralizations 200 ml of 0.1 normal NaOH is added. Then the total volume inside the beaker is 200 plus 200 200 plus 200, that is 400. So total volume is 400. However, during half neutralization, 200 ml of 0.1 normal NaOH is added and the 100 ml of 0.2 NaCl are required for the half neutralization process. So 200 ml of 0.1 normal NaOH is neutralized by 100 ml of 0.2 normal HCl. Then inside the beaker only 100 ml of HCl is remained, right? Only 100 ml of HCl remain inside the beaker because 100 ml of 0.2 normal HCl is neutralized by 200 ml of 0.1 normal NaOH. So 0.2 into 100 divided by total volume is 400 gives the answer 0.05 molar. We have to have, right? We have to have the volume of both HCl and NaOH. Total volume required for complete neutralization is 400 ml of 0.1 normal NaOH. However, for half neutralization only 200 ml is required, and this 200 ml of 0.1 normal NaOH neutralizes the 100 ml of 0.2 normal HCl. Then only 100 ml of 0.2 normal HCl is remain inside the beaker. Then we have to calculate the molarity of such 100 ml of 0.2 molar HCl present inside the beaker containing total volume of 400. Then total volume is 400 and 0.2 is the concentration of HCl and 100 is the total volume of free HCl. Then answer will be 0.05 molar. This question is based upon the half neutralization. Total volume will be 200 plus 200, 400, and the volume of free HCl is only 100 ml. We could also divide the concentration, right? 0.2 molar concentration could also divide, but in this case we have to write 200 ml of 0.1 HCl during the half neutralization. And in half neutralizations, both NaOH and HCl should be divided by 2. Both the volume of HCl and NaOH should be divided by 2. We could also divide the amount, either concentrations or either volume. We have to divide by 2 during the half neutralization. The weight of anhydrous sodium carbonate just enough to neutralize 100 ml of 0.1 m HCl will be, just use this formula, right? Very simple question. Weight in gram of base, gram equivalent weight. So normality of acid, volume in ml by thousands. We have to calculate the weight in gram of base by using this formula. And what is the equivalent weight of anhydrous sodium carbonate? That is 106 by 2. 106 is the molecular weight and 2 is the total positive charge or total negative charge in sodium carbonate. A molal solution is one that contains 1 mole of solute in 1 kg of solvent, that is 100 gram of solvent. It is known as molal solution. So this is the definition of molality also. Excess of 2 molar HCl is treated with 2.8 gram of iron as shown in the reaction, right? Then the volume of HCl consumed. We have to calculate the volume of HCl consumed here. So according to these reactions, 55.8 gram of iron combines with 2 molar of HCl. Right? What is the atomic weight of iron? That is 55.8 gram. Then HCl means 2 moles. So 1 mole of iron combines with 2 moles of HCl. 1 mole of iron means 55.8 gram because 55.8 is the atomic weight of iron which combines with 2 moles of HCl. Then 2.8 gram, here is 2.8 gram combines with 0.1 mole of HCl. Then we have to calculate 0.1 mole of HCl in volume by using this formula, because molarity is the number of moles divided by volume. So volume is equal to number of moles by molarity. Answer will be 50 cc. Molarity of KOH if its density is 1.08 gram per ml. Right? Then we have to calculate the molarity. Here is the general formula for the calculation of molarity. Weight of solute in gram 1.08, gram molecular weight of solute, that is KOH 56 is the gram molecular weight, and 1000 volume of solution in ml. Volume of solution in ml is 1.08 gram per ml, means only 1 ml, right? According to the density concept, 1.08 gram per ml means 1 ml of KOH contains 1 gram. then the volume is 1. So answer will be 19.2, but this answer is not given in the options. Right? Answer is this, right? 19.2 molar, but answer is not given in the options. So this answer is not given in the options. Right? A student in the laboratory prepares a solution by adding 1 ml of 1 mole per liter HCl to 9 milliliter of water. Then what is the total volume of the solution? 1 plus 9, that is 10. The concentration of hydronium ion HO3 plus in the solution will be. So this is the general reactions. Initial concentration of HCl is what? 1 mole per liters. So then initial volume is just only 1 ml, but the final volume is 1.9, sorry, 1 plus 9, that is 10 ml, right? 1 plus 9, right? Because 9 ml of water is added to the 1 ml of 1 mole per liter HCl, then total volume of that solution will be 10 milliliter. Then the concentration of hydronium ion is equal to 1 into 1 by 10. Just use the normality concept. So 1 into 1, N1 B1 by B2. B2 is the 10 ml total volume. So answer will be 0.1 mole per liter. Very important questions. This question was asked in BPKHS 1994. If 7.50 sample of vinegar means acetic acid, requires 37.4 ml of 0.127 normal base for neutralizations, what is the normality of the acid in the vinegar? What is the percentage by weight of acetic acid if the density of vinegar is 1.0 gram per ml? So this is very simple questions. Strength of base is 0.127 and its volume 37.4 ml. Then volume of the vinegar is 7.50. We have to calculate the strength of acetic acid in vinegar by using the normality equation, 0.63 normal octane. Then we have to calculate the percentage of the vinegar acetic acid in vinegar if density is 1.0 gram per ml. We have already discussed about this formula, right? Weight percent into density into 10 by equivalent weight. So what is the equivalent weight of acetic acid? That is 60. Molecular weight by only 1, because the basicity for acetic acid is only 1. Only one irreplaceable hydrogen is present in acetic acid, so basicity is 1. So molecular weight by 1. Molecular weight of acetic acid is 60. So the equivalent weight is 60. So yeah, here is 60. Then we have to calculate this percentage by using this equation, right? 3.78% is obtained. 0.63 normality and 3.78%. So answer might be A. The first part of the volumetric analysis has been finished, and we have solved the 50 multiple choice questions and some basic concepts related to the volumetric analysis like normality, molarity, molecular weight, mole concept, mole fractions, demol unit, etc., etc. And the next part of the volumetric analysis containing 50 more multiple choice questions from the Indian entrance examination book will be launched soon. So I will upload the video of the volumetric analysis part 2 in very near future. So you have to just wait for this. Thank you so much. Next question. Potassium permanganate reacts with ferrous sulfate according to the equations. So here is the equations of reduction of permanganate ion into Mn2 plus and the oxidation of ferrous ion into ferric ion. Here the manganese changed to Mn2 plus. The oxidation number of Mn in MnO4 minus is plus 7, right? Plus 7. Then it is changed to plus 2. And the oxidation number of iron in ferrous ion is plus 2 and in ferric ion plus 3. So plus 2 to plus 3 oxidation and plus 7 to plus 2 reductions. So here 10 ml of 0.1 molar KMnO4 is equivalent to. We have to calculate this. So we have to solve this problem on the basis of normality equation, that is number of gram equivalent of KMnO4 is equal to the number of gram equivalent of ferrous sulfate. Number of gram equivalent of KMnO4 is equal to the number of gram equivalent of ferrous sulfate. Now first calculate the number of gram equivalent of KMnO4. To calculate this, we have to convert 0.1 molar KMnO4 into normality, right? How to convert this? 0.1 into 5, 0.5. How this 5 is obtained here, right? I am going to explain about this. To convert the molarity into normality, here is the relationships. Normality is equal to n factor times the molarity, right? N factor times the molarity. What is n factors? N factor represents different things, right? In case of the calculation of equivalent weight of element, it represents valency. In case of acid, it is basicity. In case of base, acidity. In case of salt, either total positive charge or negative charge. And in case of oxidizing agent, total number of electrons gained by a molecule of potassium permanganate, right? Potassium permanganate is the oxidizing agent. So in case of oxidizing agent gains the electrons from other reactant. So how many number of electrons are gained by a single potassium permanganate here? The change in oxidation number of potassium permanganate, right? Mn in MnO4 minus is from +7 to +2. Then what is the change in oxidation number? 7 minus 2, that is 5. So this 5 is right. By gaining 5 number of electrons, MnO4 minus is changed to Mn2 plus. So this 5 is written. Then volume of the KMnO4 is 10 ml. Here is 10 ml. Then number of gram equivalent of KMnO4 is equal to n into V by 1000. N is 0.5. Volume is 10 ml divided by 1000 is equal to 0.005 gram equivalent. Now we have to source type of the option containing ferrous sulfate having 0.005 gram equivalent. So option D, 50 ml of 0.1 molar FeSO4 is equivalent to the 0.005 gram equivalent. Right? How? In case of ferrous sulfate, we have to convert this 0.1 molarity into normality. So in case of ferrous sulfate, what is the change in oxidation number? +2 to +3, that is simply 1. So in case of ferrous sulfate, 0.1 molarity is equal to 0.1 normality. Then 0.1 into 50 by 1000 is equal to 0.005 gram equivalent. So answer D is correct. Next question, an aqueous solution of glucose is 10% in strength. 10% means 10 gram of glucose in 100 ml of solution. The volume in which 1 gram mole of it is dissolved will be. The 1 gram mole of it is dissolved means 1 gram mole means 1 mole. So 1 mole is dissolved in 1 liter, right? To get the 1 molarity. 1 gram mole of glucose is dissolved in particular volume and the molarity should be 1 molar, right? Molarity should be 1 molar because 1 gram mole or 1 mole is dissolved. Then 10% strength of glucose means 10 gram of glucose is dissolved in 100 ml of solutions. Then we have to calculate the volume in which 1 gram mole of this 10% strength glucose is dissolved. Then here is the formula, 1 by volume in liters, right? 1 by volume in liter. 1 means 1 mole. 1 mole divided by volume in liter means molarity is equal to weight of solute in gram by gram molecular weight of solute into 1000 by volume of solution in ml. This is also the formula of molarity and this is also the formula of molarity because 1 mole is dissolved in certain volume in liter. So we have to equalize this. Then volume in liter, here is we have to calculate this, is equal to 1.8 liter, right? Simply by using this formula. So answer is 1.8 liter. We have to calculate source type of the volume containing 1 gram mole of 10% glucose. Effect of temperature is seen in, right? Effect of temperature is seen in only such case of concentration expressing program which involve the volume. So molality does not involve volume, W by W ratio also does not involve volume, and mole fraction also does not involve volume. So only the molarity involves volume. So effect of temperature is seen only in case of molarity. If we increase the temperature of the solution, then molarity of that solution will go on decrease, right? The molarity will go on decrease on increasing the temperature of the solution. 6.021 into 10 to the power 21 number of molecules of urea is present at NTP at 100 ml of solution. Then molarity is very simple question. We have to calculate the molarity. First of all, calculate the number of moles. Here is the formula for the calculation of number of moles. I have already discussed about this formula in mole concept chapters. So number of particles divided by Avogadro number give the number of moles. 0.01 is the number of moles. Then molarity is equal to number of moles of urea divided by volume of solution in ml into 1000. Answer is 0.1 molar. 0.1 molarity is answers, but this answer is not given in any options. right? 0.1 molar is not given here, but the answer is 0.01 mole. Number of moles of urea is 0.01 mole. Number of moles of urea divided by volume of solution in ml into 1000. It is the calculation of molarity. 0.1 molar is the answer, but answer is not given here. Next question. Rectified spirit contains 95% water and 5% alcohol by weight. Calculate the mole fraction. We have to calculate the mole fractions. So 95% of water means 95 gram of water is present in 100 gram of solution. And 5% alcohol means 5 gram of alcohol present in 100 gram of solutions, because the question gives alcohol by weight, right? 5% alcohol by weight. It is not by volume. The number of moles of water is equal to 5.28 moles, and number of moles of alcohol 0.11 mole. This 46 is the gram molecular weight of alcohol. Then mole fraction of alcohol is calculated by using this formula. This is the number of moles of alcohol divided by number of moles of water plus number of moles of alcohol. The mole fraction of water is calculated by using this number of moles of water plus number of moles of alcohol, 0.9796. So in case of mole fraction of water 0.9796, so mole fraction of alcohol is 0.0204. So answer might be C. For a 1 molar solution of sodium chloride in water at 25 degrees Celsius and 1 atm pressures, right? At these conditions, molarity is equal to normality. So molality is not equal to normality. Molality and mole fraction could not be equal, so molarity and mole fraction are not equal terms. However, molarity is equal to normality in case of sodium chloride, because the charge present in sodium chloride, in case of sodium only 1, in case of chlorine only 1. Then molecular weight divided by 1 means molecular weight and equivalent weight are same value in case of sodium chloride. So in case of sodium chloride, molarity is equal to normality, because the value of n factor is 1. Which of the following represents the meta-stable system? Meta-stable system means highly unstable. So it is an example of supersaturated solutions. Supersaturated solution is an example of meta-stable system. It is highly unstable. The solubility of a gas in water depends upon nature of gas, temperatures and pressures all. So answer will be D. These are very simple multiple choice questions. When the solute is present in trace quantity, the following expression is used. Parts per million, we have already discussed about this. What is parts per million, right? Parts per million is one of the important concept or important concentration expressing method containing solute in very low amount, trace quantities, right? After equal volume of 0.10 molar solution of ammonium sulfate and barium hydroxide have been mixed, which of the following species is present in greatest concentrations? Here is the general equations of the above problems. So if ammonium sulfate reacts with barium hydroxide, then barium sulfate will be formed. This barium sulfate will be immediately precipitated out, means it is in the solid form, right? It is in the solid form. Then barium 2 plus in aqueous form will not be available, right? Will not be available. Then the greatest concentration in the solution will be of ammonia, NH3. Barium sulfate in aqueous form will not be available. It is in solid form because it is precipitated out. However, ammonium ion could not be also found in the highest concentration, because the ammonium hydroxide is very weak base, right? Ammonium hydroxide is weak base. So NH4OH remain unionized due to its weak nature, right? Due to its weak nature, it remains unionized. Then the highest concentration would be of unionized NH3, right? NH3 aqueous means ammonium hydroxide, this one. So answer will be C. O2 and N2 are present in the ratio 1:4 by weight. Then the ratio of number of molecules, we have to calculate the number of molecules, right? If the ratio of weight of O2 and N2 is 1:4, then 32 gram of O2 contains 6.021 into 10 to the 23 molecules of O2 according to mole concept, right? This is according to mole concept. Then 28 gram of N2 contains 6.021 into 10 to the 23 molecules of N2. Then we have to calculate the ratio of number of molecules by using 1:4 ratio weight. The ratio of the weight is equal to 32/28, and ratio of number of molecule will be 6.021 into 10 to the 23 divided by 6.021 into 10 to the 23. Then the ratio of weight is 32/28. Then ratio of number of molecules will be 1:1. 1:1, this simple. Then we have to convert this ratio of the weight to 1:4, because in question 1:4 is given. Then we have to convert this ratio of weight into 1:4 by multiplying 7/32, right? By multiplying 7/32 with 32/28, then it will give the 1:4. And here also we have to multiply 1 by 1 by 7/32. The answer will be 7/32. If the ratio of the weight is 1:4, then the ratio of number of molecule will be 7:32, according to this concept. Isotonic solution apps. Isotonic solutions with same molar concentrations. Remember, this is not the normality, not density, but it is the molar concentration. This question was already asked in AFMC 1994. Isotonic solutions have same molar concentration. Next question: to convert 12 gram of sodium dihydrogen phosphate completely into sodium phosphate, then the volume of 1 molar sodium hydroxide solution required is. We have to calculate the volume of 1 molar sodium hydroxide required. Right? Here is the general reactions of above numerical problems. Then we have to go through the concept of number of gram equivalent, that is number of gram equivalent of sodium dihydrogen phosphate is equal to number of gram equivalent of sodium hydroxide. So equivalent weight of sodium dihydrogen phosphate is equal to 120/2. So 120 is the molecular weight of sodium dihydrogen phosphate. If you calculate this, then 2 is the number of replaceable hydrogen. How many number of replaceable hydrogens? 2, right? 2 number of replaceable hydrogens. So according to this equation, also 2 number of hydrogen atoms are replaced, right? So 120/2 is equal to 60. The number of gram equivalent is equal to weight in gram divided by equivalent weight. So weight in gram is 12 gram divided by equivalent weight is 60 is equal to 0.2. So this 0.2 value is equal to the number of gram equivalent of NaOH, right? So number of gram equivalent of NaOH is calculated by using this formula, N into V by 1000. So this V should be in milliliters, right? Should be in milliliters, and N into V by 1000 is equal to 0.2. 0.2 is the number of gram equivalent of sodium dihydrogen phosphate. Then V will be 200 cc, means 200 milliliter. Answer is A. Next question: the concentration of an aqueous solution of 0.01 molar methyl alcohol solution is very nearly equal to which of the following? Right? Here are different expression of concentration. Here is percentage, molality, mole fraction, and molarity. Right? So 0.01 molarity is equivalent to the 0.01 molality. Right? 0.01 molarity is very low in concentration. That is, it is very dilute solution. So in case of very dilute solution, molarity is equal to molality. So 0.01 molarity is equivalent to the 0.01 molality. So answer will be B. On dissolving 1 mole of each of the following acids in 1 liter, the acid does not give a solution of strength 1 normalis. We have to source type of the option in which molarity is not equal to normality, right? So this is 1 normal. So in case of phosphoric acid, molarity is not equal to normality. Here 1 mole dissolved in 1 liter water means 1 molar. So 1 molar is equal to 1 normal in case of HCl, perchloric acid, and nitric acid, because these 3 types of the acid have basicity 1. So molarity is equal to normality in case of these 3 acid. However, in case of phosphoric acid, molarity is not equal to normality. Normality is 3 times the molarity. We have already discussed about this. So answer will be D, phosphoric acid. In case of phosphoric acid, normality is not equal to molarity. 250 ml of a sodium carbonate solution contains 2.65 gram of sodium carbonate. If 10 ml of this solution is diluted to 1 liter, what is the concentration of the resultant solutions? So we have to find out the concentration of resulting solution. So molarity of sodium carbonate is equal to 0.1 molar by using this formula. Simply weight of solute means sodium carbonate in gram is given 2.65 gram. Gram molecular weight of sodium carbonate 106. Then 1000 by 250. because 250 ml of sodium carbonate solution contains 2.65 gram of sodium carbonate. Now then initial strength is equal to 0.2 normal. In case of sodium carbonate, the value of n factor is 2, right? Why this value is 2 in case of sodium carbonate? Because total number of charge present in sodium carbonate is 2. In case of sodium Na plus, then 2 sodium means 2 plus. So 2 plus means the normality of sodium carbonate is 2 times the molarity. So 0.2 normality. 0.1 molarity means 0.2 normality in case of sodium carbonate. Initial volume is 10 ml, right? Here is 10 ml, and it is diluted to 1 liter, that is 1000 ml. Then total volume will be 1000 ml, and initial will be 0.2, and initial volume is 10. Then answer will be 0.002 normality. It means 0.001 molarity. It is very simple questions. We have to just know the formula, right? This formula is very important. We have to know this formula, and we have to calculate the strength of 10 ml sodium carbonate solution first of all by using this formula. Then we have to convert these concentrations into normality by using this concept. Next question, mixture X is equal to 0.02 mole of pentaamine sulfo cobalt third bromide. This is the IUPAC name of this compound, and 0.02 mole of pentaamine bromo cobalt third sulfate was prepared in 2 liter of solution. Then 1 liter of mixture X, this is the mixture X, plus excess silver nitrate gives Y, and 1 liter of mixture X plus excess barium chloride gives Z. Then we have to calculate the number of moles of Y and Z, right? We have to calculate number of moles of Y and Z. This compound plus this compound, if silver nitrate is added to the solution contain these two compounds, then silver bromide is precipitated out, right? Only this compound will react with silver nitrate for the precipitation of silver bromide, because silver nitrate reacts with bromide ion for the precipitations of AgBr. It does not react with sulfate ion to give the precipitations. So only such type of the ion which is outside the larger bracket is going to be reacted with the silver nitrate. So AgBr is precipitated out, SO4 does not react. In case of these mixtures, if we add barium chloride, then barium chloride reacts with only sulfate. It does not react with the bromide ion, because bromide ion is outside the bracket, and the ion present inside the bracket is not reacted with the either silver nitrate or barium chloride. Only such type of the ion which is present outside the larger bracket. These ions present inside the larger bracket are unionizable in case of complex, right? Only such type of the ion which are present outside the larger bracket are known as ionizable. They are ionized. So in case of barium chloride, only barium sulfate is precipitated. Now, according to the question, 2 liters of solution contains 0.02 moles of pentaamine sulfo cobalt third bromide, right? 2 liters of solution contains 0.02 mole. Then 1 liter of solution contains 0.01 mole, because in this reaction only 1 liter of mixture X is used. Then Y is equal to 0.01 mole, because this mixture contains only 0.01 mole of this compound. Then Y will be AgBr. Y will be AgBr. It will be 0.01 mole only. Then in case of 2 liters of solution contain 0.02 mole of these compounds, in this case, then 1 liter solution contain only 0.01 mole. Then answer will be 0.01 mole. Then Z will also be 0.01 mole. So answer will be A, both will be 0.01 mole, because only such type of the ions which is outside the bracket will be precipitated out, right? Another type of the ions which are inside the larger bracket of the complex bracket, right, are not ionizables. This is the main concept. Answer will be A. It is very simple. Silver nitrate reacts only with the bromide ion, and barium chloride reacts only with the sulfate ion. Next question, molality is the most inconvenient unit for expressing concentration because it involves the measurement of liquid. We could easily measure the volume of the liquid, but it is very difficult to measure the weight of the liquids. So while in the case of molality, it requires the measurement of weight of liquid, it is inconvenient. The mole fraction of water in 20% aqueous solution of hydrogen peroxide is. We have to calculate the mole fraction of water in 20% aqueous solution of hydrogen peroxide. 20% aqueous solution of hydrogen peroxide means 20 gram of H2O2 is present in 100 ml of aqueous solution. Means 100 minus 20 gives the 80 gram of water, right? 80 gram of water. So 20% means in 100, 20 gram is of hydrogen peroxide, then 80 gram is of water. The number of moles of water will be 80 by 18. 80 is the amount of water and 18 is the molecular weight, then 4.44 moles. Similarly, number of moles of hydrogen peroxide is 0.59 mole. Then mole fraction of water is 0.88. In another case, by using this formula, we could also calculate it. If we do not convert this ratio value into decimal unit, then we use this formula. So answer is 68 by 77. 68 by 77 means 0.88. Azeotropic mixtures are, right? Azeotropic mixtures are known as constant boiling mixtures, right? Azeotropic mixtures of the two liquid which boil at a constant temperatures and can be distilled unchanged in their composition are called the azeotropic mixtures. So azeotropic mixtures contain two types of liquids which have different boiling point in their single state, but when they are in mixture conditions, their boiling point will be now constant. There are two types of azeotropic mixtures: maximum boiling azeotropes and minimum boiling azeotropes. So maximum boiling azeotropes boiling points are more than either of the two pure components, right? Example, nitric acid and waters. So nitric acid and water both have not the same boiling point, however their mixture have same boiling point, that is 393.5 Kelvin. Water has one boiling point and nitric acid is another boiling point, however their mixture have single boiling point, that is 393.5 Kelvin. Non-ideal solution will show the negative deviations, right? It is prepared by using source type of the non-ideal solutions which shows the negative deviation. Minimum boiling azeotropes boiling points are less than the either of the two pure components. In case of the azeotropic mixtures of minimum boiling cases, then the boiling points will be less than the either of the two pure component. Example, ethanol and water, right? Ethanol 95.5% and water 4.5%. It is also known as rectified spirit. So it is also an important example of azeotropic mixtures. The boiling point of ethanol is around 78 and water is around 100. However, boiling points are less than the either of the two components. So this value will be less than the boiling point of ethanol and boiling point of water. So this is all about azeotropic mixtures. This one is important, rectified spirit. 25.3 gram of sodium carbonate is dissolved in enough water to make 250 ml solution. If sodium carbonate dissociates completely, then molar concentration of sodium ion and carbonate ions are respectively. We have to calculate the molar concentration of sodium ion and carbonate ion. First of all, calculate the sodium carbonate concentrations in molarity. So we have to calculate the concentration of sodium carbonate in molarity. Here is the formula, right? We have already discussed about this formula. Then 25.3 is the weight of sodium carbonate, 106 is the molecular weight of sodium carbonate, 1250 is the volume. Then concentration will be 0.9547 molar sodium carbonate. Then in aqueous solution, this sodium carbonate will go on ionization process. So sodium carbonate will get ionized to give 2 Na plus and 1 carbonate ion. Then what is the concentration of 2 Na plus? 1 mole of Na2CO3 gives 2 mole of sodium ion and 1 mole of carbonate, means 1 molar sodium carbonate is equal to 2 molar sodium ion and 1 molar carbonate ion. Then 0.9547 into 2 is the concentration, molar concentration of Na plus, that is 1.910 molar, and in case of carbonate ion 0.9547 molar. So we have to multiply by 2 in case of sodium and we have to put just as it is in case of carbonate. Answer will be C. Of 5.2 molal solutions, right? It is molal, not molar. Aqueous solutions of methyl alcohol is supplied. What is the mole fraction of methyl alcohol in the solution? So we have to calculate the mole fraction of methyl alcohol in the solution. So here is the general formula of the calculation of mole fraction of alcohol: number of moles of alcohol plus number of moles of water. Then question is given in the form of molality. So here is the general expression or the relationship between molality and the mole fraction. We have already discussed about this, and this formula is obtained according to this process, and x1 is equal to m by 55.5 plus m. M is the molality and 55.5 plus m is the molality of the methyl alcohol. So answer will be 0.0857. So this formula is obtained according to this process, right? Just remember this formula, which shows the relationship between mole fraction and the molality. We have already discussed about this formula. Next question: the density of a solution prepared by dissolving 120 gram of urea in 1000 gram of water is 1.15 gram per milliliter. Then molarity of the solution. We have to calculate the molarity of the urea solution. So to calculate the molarity, first of all we have to calculate the volume of solution. Volume of solution is not given here, right? We have to calculate the volume of the solution. So how to calculate the volume of the solution? By using the density concept. So this 1.15 gram per ml is the density of the solution, right? So that solution contains 120 gram of urea and 1000 gram of water. So total mass will be 1000 plus 120 divided by density gives the volume. So rho is equal to m by b. Rho means density is equal to mass by volume. Then volume is equal to mass by density. Here is the total mass of the solution, 1000 plus 120, and 1.15 is the density of the solution. So 973.91 milliliter is the volume of the solution. Then by using this formula we could easily calculate the molarity of urea, and gram molecular weight of urea is equal to 60, because 60 is the gram molecular weight of urea. That is, molecular weight of urea is 60. Simple. When the crystal of the solute is introduced into a supersaturated solution of the solute, then the excess of solute will be crystallized out. Supersaturated solution means it is already supersaturated, means no more solute should be added on that supersaturated solution. If you add another type of solute in the supersaturated solution, then the excess of solute will be immediately crystallized out, because no more solute could be added on the supersaturated solution to make it further solution. Volume of 0.1 molar potassium dichromate required to oxidize 35 ml of 0.5 molar FeSO4 solution is, right? We have to calculate the volume of 0.1 molar potassium dichromate. So first of all, convert this 0.1 molar into normality. In case of potassium dichromate, equivalent weight is equal to molecular weight by 6. Then normality will be 0.1 into 6, 0.6. So we have already discussed normality is equal to n factor times the molarity, right? N factor times the molarity. So what is the value of n factor? 6. The normality will be 0.1 into 6. In case of ferrous sulfate, so molecular weight by 1, ferrous sulfate 0.5 normal, 0.5 molar will be equal to 0.5 normal. This is an important example of redox titrations. Here potassium dichromate is an oxidizing agent which oxidizes the ferrous sulfate into Fe3+. So the change in oxidation number of Fe ion will be 3 minus 2, only 1. In case of potassium dichromate, this Cr2O7 2 minus dichromate ion changes to Cr3+, right? Cr3+. Then what is the total change in oxidation number? 6. Then what is the change in oxidation number for only one Cr atom? That is only 3. For the 2 chromium atom, 6. So answer will be 0.6 normality. Very important question. Then go through the concept of number of gram equivalent equalizations. Number of gram equivalent of potassium dichromate is equal to the number of gram equivalent of ferrous sulfate. Then 0.6 into V. V means the volume of the potassium dichromate solutions. Then 0.6 is the normality, and 0.5 is the strength of ferrous sulfate. It is in normality, into 35 is the volume divided by 1000. Answer will be 29.2 milliliter. Answer is A. This question is very important. We have to just convert the molarity into normality, right? We have to convert the molarity into normality. Next question. 20 ml of 0.02 molar potassium permanganate was required to completely oxidize 10 ml of oxalic acid. Then we have to calculate the molarity of oxalic acid solutions, right? This is the general reactions of the above problem. Then we have to convert this 0.02 molarity into normality, right? Equivalent weight of KMnO4 in acidic medium is equal to molecular weight by 5. This 5 is the N factor. Then 0.02 into 5 means 0.1. 0.1 normal is the normality of the KMnO4. The number of gram equivalent of KMnO4 solution is equal to the number of gram equivalent of oxalic acid solutions. So 0.1 is the normality of KMnO4, 20 is the volume of KMnO4 divided by 1000 is equal to 10. This is the volume of oxalic acids into N is the normality of oxalic acid, which we have to calculate is given by 0.2 normal is equal to 0.1 molar. This is also based upon the relationship between normality and molarity. So equivalent weight of oxalic acid is equal to molecular weight by 2. So how this 0.2 is converted into 0.1? Let's examine about this. Normality is equal to N factor times the molarity, right? So in case of oxalic acid, what is the value of M factor? That is 2. N factor is 2. Then molarity is equal to N by N. Then N is equal to 0.2 divided by N means 2. 0.2 by 2 is equal to 0.1. Right? 25 ml of a solution of barium hydroxide on titration with 0.1 molar HCl gave a titer value of 35 ml. What is the molarity of barium hydroxide? Right? Titer value means HCl, the solution which is kept in what? Conical flask. The solution which is kept in conical flask is known as titer. Then barium hydroxide plus 2HCl, BaCl2 plus 2H2O. Then equivalent weight of barium hydroxide is molecular weight by 2 because number of replaceable OH minus is 2. Number of replaceable OH minus is also known as acidity. So in case of barium hydroxide, what is the value of acidity? Is 2. So molecular weight by 2. The number of gram equivalent of barium hydroxide is equal to number of gram equivalent of HCl. Then this is the normality of barium hydroxide. We have to calculate this, and 25 is the ml. 25 ml of a solution of barium hydroxide divided by 1000 is equal to 0.1. 0.1 is the normality of HCl. In case of HCl, 0.1 molarity is equal to normality into 35. 35 is the titer value, that is HCl solutions divided by 1000. Answer will be 0.1 for normality, and it should be converted into molarity 0.07. 0.1 for divided by 2. These two, right? This is known as N factor. Next question. How many kilograms of wet NaOH? Remember, this is wet NaOH, not in powder form, containing 12% water are required to prepare 60 liters of 0.50 normal solutions. This is the formula of normality, and we have to prepare the 0.50 normal. So put the value 0.50 here. Then volume of solution in ml should be 60. Liter means 60 into 1000. And gram equivalent weight of NaOH is 40. Then we have to calculate weight of NaOH in gram. And answer will be 1200 gram by using this formula. It is equal to 1.2 kilogram. Then percentage of NaOH in aqueous solution is only 88% because 12% is water. This wet NaOH contains 12% water. Then the weight of NaOH in aqueous solution is 88%, right? Then weight of this wet NaOH which is required is 1.36 kg. Remember, if NaOH is in powder form, that it contains only NaOH, no any water, then the 1.2 kg is sufficient to produce 60 liters of 0.50 normal solution. However, the given wet NaOH contains 12% water. 12% water means it contains only 88% of NaOH. Then the 88% NaOH containing wet NaOH should be in higher value than the 1.2 kg. Answer will be 1.36 kg of wet NaOH. The amount of wet NaOH should be higher than the 1.2 kg value because this 1.2 is in anhydrous form or in powder form, and then wet NaOH is in aqueous form which also contains 12% water. Very important question. 1 liter of sample of seawater is found to contain 0.0015 gram of dissolved oxygen. Calculate the concentration of dissolved oxygen in seawater. We have to calculate the concentration of oxygen in seawater in ppm, right? ppm is formula weight of dissolved oxygen divided by weight of seawater into 10 to the 6. Weight of dissolved oxygen is equal to 0.0015 gram. Here it is. Then weight of seawater. So weight of seawater is equal to density of seawater times the volume, right? The volume of seawater is 1000 ml. 1 liter means 1000 ml. That 1000 into 1.1 give the total weight of seawater. So 1000 into 1.1, answer will be 1.36 ppm. We have to convert this 1 liter into weight or mass by using this concept, density of seawater, 1.1 gram per cc. 0.4 gram of metal is dissolved in 50 cc of 0.64 normal HCl, and the solution is diluted to 100 cc, right? And 25 cc of the solution is then required 27.3 cc of 0.11 NaOH for neutralization. Then we have to find out the equivalent weight of that metal. First of all, calculate the strength of that diluted acid solution, that is 100 cc solution. According to the normality equations, 27.3 into 0.11, right, divided by 25, this is according to the normality equations, very simple, is equal to 0.12 normal diluted acid solutions. So the strength of this 100 cc diluted acid solution is equal to 0.12 normal diluted acid solution. And then 100 cc of 0.12 normal diluted HCl solution is equal to 12 cc of 1N HCl solution. Just multiply this 100 by 0.12. Then answer will be 12 cc of 1N HCl solution. It means 100 cc of 0.12 N diluted HCl solution is equal to 12 cc of 1N HCl solutions. Then 50 cc of 0.6 N HCl solution is also equal to 32 cc of 1N HCl solution, right? Then the volume of acid solution which is consumed by metal is equal to 32 minus 12, right? 32 minus 12 is equal to 20 cc of 1N HCl solution. Remember, right? This 32 cc of 1N HCl solution is the initial HCl solutions. Then the final HCl solution is equal to 12 cc of 1N HCl solution which remains in free state, right? 12 cc of 1N HCl solution is free, which is not attacked by the metal. So 12 cc of 1N HCl solution is not reacted with the metal. Only 20 cc of 1N HCl solution reacts with the metal. We have to find out how much volume of 1N HCl reacts with the metal, that is 20 cc, because 12 cc of 1N HCl solution is free in the solution. Then 20 cc of 1N HCl consumes 0.4 gram of metal according to the question, because 20 cc of 1N HCl consumes 0.4 gram of the metal. Then 1000 cc of 1N HCl consumes equivalent weight of that metal. So 20 is the equivalent weight. So 1000 cc of 1N HCl consumes how much amount? That will be the equivalent weight of that metal. This question should also be solved on the basis of this formula. We have to go through the number of gram equivalent concept. Number of gram equivalent of metal plus number of gram equivalent of diluted acid, this 100 cc, is equal to number of gram equivalent of the concentrated acid solutions, right? By using this concept, we could also solve this problem. This question is very important. Next question is generated in stomach. Then the doctor prescribes him antacid. Antacid contains the base. By taking 3 antacid tablets, the strength of acid decreases from N by 10 to N by 100. If the fluid material is 1000 cc, means 1 liter, then we have to calculate the amount of base present per antacid tablet. Equivalent weight of the base present in antacid is equal to 100. Now, 1000 cc of N by 10 acid solution means 100 cc of 1N acid solution. Just multiply 1000 by 0.1. Then answer will be 100 cc of 1N acid solution. We have to convert these two strength into same strength, that is 1 normal. Then 1000 cc of N by 100 acid solution is equal to 10 cc of 1N acid solution. Means by taking the antacid tablets, the strength of acid solution goes on decrease. That means the volume of 1N acid solution also goes and decreases from 100 cc to 10 cc. Then the volume of the acid solution having one normal concentration decreased by antacid is equal to 90 cc. That is 100 minus 10. Initially 100 cc of 1N acid solution is present in the stomach. Then after the consumptions of that antacid, 10 cc of 1N acid solution is remained. Then how much amount or how much volume is consumed by the antacid? 90 cc, 100 minus 10. Then according to equivalence concept, 1000 cc of 1N acid solution neutralizes the equivalent weight of the base. What is the equivalent weight of the base? 100. Then 90 cc of acid solution, here is 90, neutralizes 9 gram of base. Then 9 gram of base is present in 3 antacid tablet because the person takes 3 antacid. Then 1 antacid tablet contains only 3 gram of the base. Answer is 3 gram. This question is also important. We have to just convert this n by 10 and n by 100 into 1 normal so that we could easily calculate the volume of the acid consumed by the antacid tablets. 25 cc of an alkali solution is mixed with 10 cc of 0.75 N acid solution. Right? And for complete neutralization, it further required 20 cc of 0.8 normal acid solution. Then find the strength of the given alkali solution. We have to calculate the normality of the alkali solutions. Right? Just we have to calculate the normality of the alkali solution because this alkali solution requires two different types of acids. Right? One is 0.75 normal acid solution, another is 0.8 normal acid solutions. Then 10 cc of 0.75 N means 7.5 cc of 1N acid solution. Similarly, in another case, 16 cc of 1N acid solution. Then how much volume of acid solution is consumed up by these alkali solutions having 1N acid? Total volume of the acid solution mixture will be 7.5 plus 16, 23.5 cc of 1N acid solution. To add these two volume, we have to convert the strength in same unit, right? Here is 0.75 N, here is 0.8 N. We have to convert this into one normal, only that we can add it. That is 23.5 cc of 1N acid solution is required for the complete neutralization of this 25 cc of an alkali solutions. Now, volume of the acid solution mixture 23.5 cc and the strength will be 1 normal, right? Here is 1 normal. And the volume of the alkali solution is equal to 25. Then we have to calculate the normality of the acid solution mixture. Sorry, we have to calculate the normality of the alkali solution mixture, not the acid solution, right? Alkali, right? Alkali solution mixtures is equal to 23.5. Here is 23.5 into 1 divided by 25. 25 is the volume of alkali solution, right? So it is the strength of alkali solution mixture, not acid solution, right? Alkali solution. Answer is 0.94 normal. 100 ml of 0.1 m HCl is mixed with 75 ml of 0.1 m NaOH, right? HCl is mixed in NaOH. What is the molarity of resulting solution with respect to the acid and the salt form, right? Here is the general representations of the above problem. NaOH plus HCl gives NaCl plus water. 100 ml of 0.1 m HCl is given. In case of HCl, molarity is equal to normality. So 10 ml of 1 m HCl, 75 ml of 0.1 m NaOH, 7.5 ml of 1 m NaOH. We have to just give, or we have to make the same strength of both NaOH and HCl so that we can add or subtract. After the reactions, 2.5 ml of 1 m HCl is left right here. 1 m HCl solution having volume 10 ml. Then 1 molar NaOH solution having volume 7.5 ml. Then how much volume of the acid is left after the completion of the reaction? 10 minus 7, right? 10 minus 7. That is 2.5 ml of 1 m HCl is left. Then how much amount of NaCl is formed? 7.5 ml of 1 m NaCl is formed based upon the limiting reactant concept, which is in low amount. 7.5 ml of 1 m NaOH is low in amount. So according to these reactions, NaOH is in 7.5. However, HCl is in 10 ml. Then 7.5 ml of NaCl will be formed, not 10 ml of NaCl. 7.5 ml of 1 m NaCl is formed, right? So total volume will be 175 ml. That is 100 plus 75. 100 ml of 0.1 MaCl and 75 ml of 0.1 MnS. Then total volume will be 175. Then we have to calculate the molarity of HCl left, that is 2.5 into 1 divided by 175 is equal to 0.0143 molar. Then molarity of NaCl. So how much volume of sodium chloride is formed? 7.5 ml, because sodium chloride is formed according to the volume of the NaOH, because NaOH is the limiting reactant here. Then 7.5 ml of 1 m NaCl, 7.5 into 1 divided 175. We have to calculate the molarity of NaCl in the whole solution. The whole solution contains how much volume? 100 plus 75, that is 175 is equal to 0.0429 molarity. This question is very important, right? 100 ml of 0.1 molar NaOH is titrated against the 0.1 molar HCl taken in the burette. What is the molarity of resulting solution when the alkyl is half neutralization? This question is also based upon the half neutralization concept. We have already discussed about the half neutralization concept, right? Half neutralization. Also find the concentration of salts in mole per liter, right? We have to find out the concentration of salts. This is the general representation. So volume of 0.1 m HCl required for complete neutralization is equal to 0.1 into 100 divided by 0.1 based upon the normality equations. So how much volume of 0.1 m HCl is required for the complete neutralization of NaOH? That is 100 ml, right? This is simple according to normality equation. Then volume of 0.1 molar HCl which is required for half neutralization will be only 50 ml, right? Only 50 ml, because 100 ml of 0.1 m HCl is required for the complete neutralization, but only for the half neutralizations 100 by 2 ml of 0.1 m HCl is required. Then the total volume of the solution inside the conical flask will be 100 plus 50, right? 50 is the volume of the HCl added. Here is NaOH. I will recall this point. Here is NaOH. Inside the beaker, NaOH is present. Then how much amount NaOH? 100 ml, right? 100 ml of NaOH is present inside the beaker. Then during the half neutralizations, 50 ml of HCl is added. Then total volume will be 100 plus 50, that is 150. Then we have to calculate the molarity of the resulting solution when the alkyl is half neutralized, right? So we have to calculate the molarity of solutions here. What is the molarity of the solution present inside the beaker? Total volume will be 150. Then volume of 0.1 molar NaOH remained after half neutralization will be only 50 ml, because total volume is 100 ml. Then about 50 ml is neutralized by the NaOH, right? Sorry, HCl. Total volume of NaOH here is 100. Among 100, 50 ml is neutralized by the HCl during half neutralization. Then only 50 ml is here present after the half neutralization. After half neutralization, only 50 ml of NaOH is present, but the total volume is 150 ml. Then the strength of resulting solution is equal to 0.1, right? 0.1 is the normality of the sodium hydroxide, or molarity. Simple. In case of sodium hydroxide, molarity is equal to normality. So 0.1 is the molarity of sodium hydroxide into 50 is the total volume of the sodium hydroxide present here after the half neutralizations, and this 150 is the total volume of the solution. So answer will be 0.033 molar. Since only 50 ml of 0.1 m HCl was dropped from the burette, right? Here from the burette only 50 ml of 0.1 m HCl was dropped, because the alkali is only half neutralized. For the half neutralizations, only half of the total volume required is dropped inside the beaker or inside the conical flask. Then 5 ml of 1 molar NaCl will be formed. Just multiply this. 50 into 0.1, right? 50 into 0.1 divided by 150 will be 0.033 molar. Answer will be 0.033 molar. So this question should be solved on the basis of limiting reactant concept, right? How to find the strength of salt? Strength of salt, this is the salt formed. It mainly depends upon the volume of HCl added, because HCl is added here. HCl is the limiting reactant in the sense that, right? So amount of NaCl formed will mainly depend upon the amount of HCl dropped, because HCl is dropped to only 50 ml. However, 100 ml of 0.1 molar NaOH is already present here. Then the amount of NaCl formed will mainly depend upon the 50 ml of 0.1 m HCl. That is 50 into 0.1 divided by 150 is equal to 0.033 molar. Very important questions. A piece of aluminium weighing 2.7 gram is heated with 75 ml of H2SO4. Specific gravity 1.18 and 24.7% by weight. After the metal is carefully dissolved, the solution is diluted to 400 ml. Calculate the molarity of free H2SO4 in the resulting solution, right? We have to calculate the molarity of free sulfuric acid present in the resulting solutions. First of all, calculate the normality of sulfuric acid by using the concept of specific gravity and weight percentage. Answer will be 5.95 normal. Then 75 ml of 5.95 normal H2SO4 means 446.25 ml of 1N H2SO4. Here is, we have to calculate the strength of 75 ml of H2SO4, that is 5.95. Then 5.95 normal 75 ml of H2SO4 is equal to 446.25. Just multiply this 75 into 5.95. The strength of diluted H2SO4 solutions, right? We have to calculate the strength of diluted H2SO4 solutions. After the metal is carefully dissolved, the solution is diluted to 400 ml. We have to calculate the strength of these 400 ml acid solutions is equal to 446.25 into 1, right? 1 is this 446.25 into 1 divided by 400 based upon the dilution formula 1.1156 normal. The strength of this diluted acid is equal to 1.1156 normal. Now 400 ml of 1.12 or 1.1156 normal H2SO4 is present in the solutions, right? 400 ml of 1.12 normal H2SO4 is present in the solution. Now 9 gram of aluminum consumes 1000 cc of 1N H2SO4 based upon the concept of equivalent weight. 9 is the equivalent weight of aluminum, so it will consume 1000 cc of 1N H2SO4. Then 9 gram of aluminum consumes 1000 by 1.1156 is equal to 896.38 cc of 1.1156 normal H2SO4, because the strength of 400 ml acid solution is only 1.1156, right? We have calculated this 1.1156, right? 1.1156. Then 2.7 gram is given here. Aluminum consumes 268.91 cc of 1.12 normal H2SO4. Now we have to calculate the free H2SO4 present in the solutions, right? Total H2SO4 present in the solution is 400 ml, right? 400 ml of 1.12 normal, right? 400 ml of 1.12 normal H2SO4 is present in the solution. Then 400 minus 268.91 cc gives the volume of the free H2SO4 present in that solution, right? How to know this about the 268.91 cc of 1.12 normal H2SO4 is consumed by the 2.7 gram of aluminum. Then free H2SO4 will be 400 total volume minus the volume of H2SO4 consumed by the aluminum is equal to 131.09 cc of 1.1156 normal H2SO4. Then we have to calculate the strength of this volume H2SO4 present in 400 ml. 131.01 into 1.1156 divided by 400 is the total volume. Answer will be 0.1828 molarity. 0.3656 normal is equal to 0.1828 molarity. This question is very important. We have to solve this question by using different types of formula. First one is specific gravity. Second one is normality equation. Third one is gram equivalent concept. Very important, right? 2.8 cc of chamber acid means sulfuric acid, is made to a liter solution. 50 cc of this solution neutralize 38.2 cc n by 10 sodium carbonate solution. Then we have to find out the percentage of sulfuric acid in the chamber acid if its specific gravity be 1.71. Now concentration of diluted chamber acid solution is equal to 38.2 into 0.1. This one is 38.2 into 0.1 divided by 50, right? So this equation is based upon the normality equation. 38.2 into 0.1 by 50 gives the concentration of these diluted chamber acid solutions 0.0764. Then initial concentration is 0.0764 into 1000 by 2.85 gives the initial concentration of that chamber acid, right? What is the initial concentration of chamber acid? That is 226.81 normal. by using the normality equation. What is the normality of this 50 cc of solutions? 0.0764, right? 0.0764, and 22.85 cc of initial chamber acid solution is made to 1 liter, means 1000 ml. Then the initial concentration will be 26.81. Just use the normality equation in two steps. First one is this and second one is this. Then we have to calculate the weight percent by using this formula. Normality is equal to weight percent into density into 10 by equivalent weight. 49 is the equivalent weight of sulfuric acid and 26.81 is the concentration of that chamber acid initially. Then answer will be 76.81%. Very important question. We have to use the two formula, normality equations and the percentage compositions or weight percent method. 3.12 gram of washing soda crystals were dissolved in 200 cc of water. 20 cc of the resulting solution is titrated with N by 10 H2SO4, required 21.8 cc for exact neutralization. Calculate the percentage of anhydrous sodium carbonate. We have to calculate the percentage of anhydrous sodium carbonate in the crystals. So how to calculate the percentage of anhydrous sodium carbonate? We have to know how much amount of pure washing soda is present in the 3.12 gram of washing soda. 3.12 gram of washing soda contains some of the impurities. So only pure washing soda reaction here with the H2SO4, right? Strength of diluted washing soda solution is equal to 21.8. Here is 21.8 into 0.1 divided by 20, right? 20 is equal to 0.109 because washing soda were dissolved in 200 cc of water. Then this concentration of 200 cc of washing soda solution is equal to 0.109 based upon the normality equations of 21.8 into 0.1 divided by 20 gives the concentration of this 200 cc washing soda solution. Then pure weight of sodium carbonate in the solution is equal to NEB by 1000. This formula is also important. This is the normality, equivalent weight, and this is volume. So answer will be 1.16 gram. 53 is the equivalent weight of washing soda. Then 200 is the volume of the diluted solutions. Then answer will be 1.16 gram, right? This is the pure weight of sodium carbonate. Then percentage of anhydrous sodium carbonate is equal to 1.6 divided by 3.12. 1.16 divided by 3.12 into 37.03%. This question is very important. We have to just find out the weight of pure washing soda by using this formula. First of all, calculate the strength of washing soda, and by using the formula NEB by 1000 we could easily calculate the pure weight of sodium carbonate. If you find the pure weight of sodium carbonate, then we could easily calculate the percentage of anhydrous sodium carbonate in the crystals. The pink color of phenolphthalein in alkaline medium is due to negative form. We have already discussed about this by using this formula. HPH is the general representations of the phenolphthalein, and if it ionizes, then pH minus plus H plus, and this pH minus gives the pink color. Then it is in negative form. I have already discussed about this, right? If question is asked about the methyl orange, then answer will be positive form. Next question, 0.5 gram of a mixture of ammonium chloride and sodium chloride was boiled with 25 ml of 0.95 normal NaOH in a conical flask till the ammonia is expelled. Right? The residual solution was cooled and the made to 100 ml. It was found that 10 ml of the diluted solution utilized 16 ml of standard H2SO4 N by 10 solution. F is the normality factor, which is equal to 1.06, and calculate the percentage of pure ammonium chloride in the mixture. Here is a mixture of ammonium chloride and sodium chloride, right? And the reaction between ammonium chloride and sodium chloride with sodium hydroxide. Sodium chloride does not react with the sodium hydroxide. So ammonium chloride only reacts with the sodium hydroxide. So we have to find out the amount of ammonium chloride present in the mixture. So strength of diluted residual NaOH solutions is equal to 16 into 0.1. Here is 16 into 0.1 into 1.06. This is normality factor, and we have to multiply this N by 10 by normality factor. So 16 into 0.1 into 1.06 divided by 10. Where is 10? this one is 10. So by using this formula, normality concept, we will easily calculate the strength of this 100 ml NaOH solution, that is 0.17 normal. So 100 ml of 0.17 normal NaOH solution means 70 ml of 1 NaOH solution. Just multiply 100 into 0.17. Then 25 ml of 0.95 NaOH solution. Here is 25 ml of 0.95 NaOH solution is equal to 23.75 ml 1 NaOH solution. So what is the initial concentrations or initial amount or initial volume of 1 NaOH solution? 23.75. But the remaining volume will be 17 ml. So this 17 ml of NaOH solution is remained after the complete reaction of NaOH with the ammonium chloride, right? This one is remaining volume. Then how much amount is consumed by the ammonium chloride? 23.75 minus 17, that is 6.75 ml of 1 NaOH is consumed by ammonium chloride. Then 1000 ml of 1 NaOH means 53.5 gram of ammonium chloride. This 53.5 is the equivalent weight of ammonium chloride. So 1000 ml of 1 NaOH is equal to 53 gram of ammonium chloride. So this is based upon the number of gram equivalent concept. Number of gram equivalent of NaOH is equal to number of gram equivalent of ammonium chloride. Then 6.75 ml of 1 NaOH consumes 0.36. Then 0.36 gram is present in the mixture. So 72% is the percentage of ammonium chloride in the mixtures. So we have to calculate the percentage of ammonium chloride present in the mixtures. So 0.36 is present in the whole solution or whole mixture. Then 0.5 is the total mixtures. So remaining is sodium chloride. So 0.36 gram of ammonium chloride is present in 0.5 gram of the mixtures. Then what is the remaining weight? Remaining weight is of sodium chloride. This question is also important. Next question, 1.4 gram of a mixture of calcium carbonate and magnesium carbonate was dissolved in 200 ml of 0.2 normal HCl solution. After the reaction was complete, the resulting solution was diluted to 250 ml and 10 ml of the solution required 12 ml of N by 30 NaOH. Then we have to calculate the percentage composition of the mixture. That is, what is the amount of calcium carbonate and what is the amount of magnesium carbonate, right? So what is the strength of dilute HCl solutions? That is 12 into 0.033 divided by 10. So what is the strength of this 250 ml of acid solution? That is 0.04 normal. 250 ml of 0.04 normal dilute HCl solution means 10 ml of 1 NaCl solution, right? Just multiply 250 by 0.04. Then 200 ml of 0.2 normal HCl solution. Initially 200 ml of 0.2 normal HCl was given. That is equal to 40 ml of 1 NaCl. Just multiply 200 by 0.2. Then initially 40 ml of 1 NaCl was in the mixtures. Then only 10 ml of 1 NaCl solution is left. Then how much volume is consumed by these mixtures? That is 40 minus 10. So 30 ml of 1 NaCl is consumed by this mixture. Then we have to calculate the weight of that mixtures. Here are different component. One is calcium carbonate and the magnesium carbonate. Then let the weight of calcium carbonate in the mixture is x. Then the magnesium carbonate will be 1.4 minus x. Then use the concept of number of gram equivalent. Number of gram equivalent of calcium carbonate plus number of gram equivalent of magnesium carbonate is equal to number of gram equivalent of that 1 NaCl used by the mixtures. That is N into B by 1000. N is the 1, B means 30 ml. Here is 30 divided by 1000 is equal to x by equivalent weight of calcium carbonate 1.4 minus x by equivalent weight of magnesium carbonate. And by calculating, the value of x will be 0.875 gram. We have to know the equivalent weight of calcium carbonate, that is 50, and equivalent weight of magnesium carbonate is equal to molecular weight of magnesium carbonate divided by 2. Then by using the equations, x will be 0.875 gram and x is the amount of calcium carbonate. Then weight of magnesium carbonate will be 1.4 minus 0.875, that is 0.25. Then total amount of mixture is 1.4 gram. So 0.875 divided by 1.4, 62.5% of calcium carbonate and 37.5% of magnesium carbonate, right? 0.525, right? This is 0.525. It is not 0.525. 1.4 minus 0.875 is equal to 0.525. This is not 0.25, this is 0.525, right? This is right, 0.525. Next questions, find the equivalent weight of phosphoric acid in the reactions, right? We have to find out the equivalent weight of phosphoric acid in the reaction, right? Calcium hydroxide plus phosphoric acid is equal to calcium hydrogen phosphate plus 2H2O. Among three hydrogen atoms present in the phosphoric acid, how many number of hydrogen atoms are present in phosphoric acid? 3. So among these three, only 2 hydrogen atoms are replaceable according to this reactions. In this reaction, only 2 hydrogen atoms are replaceable. Only 2 hydrogen atoms have been replaced. So the basicity of phosphoric acid will be 2. Then the equivalent weight is equal to molecular weight by basicity. Answer will be 49. What volume NTP of gaseous ammonia will be required to be passed into 30 ml of 1 normal H2SO4 solution to bring down the acid strength of the solution to 0.2 normal, right? 30 ml of 1N H2SO4 is converted to 0.2 N of normal solutions. Then volume of the acid neutralized by NH3 is equal to 30 ml of 0.8 normal H2SO4 because the strength has been decreased from 1 normal to 0.2 normal. So what is the difference of 1 minus 0.2? That is 0.8. So volume of acid neutralized by NH3 is equal to 30 ml of 0.8 normal, right? It is not 30 ml of 1 or 30 ml of 0.2. It is 30 ml of 0.8 normal H2SO4. Then according to this equations, we have already discussed about these equations. Weight in gram of NH3 is equal to 0.408 gram. This is normality of the acid and this is volume of the ml and this is 1000, right? Volume in ml of acid. What is volume of acid in ml? That is 30 ml into normality of acid is equal to 0.8. So 0.8 into 30 divided by 1000. So what is the gram equivalent weight of ammonia? So we have to calculate the gram equivalent of ammonia, that is 17. So weight in gram of ammonia will be 0.408. Then 8 NTP 17 gram of NH3 occupy 22.4 liters. Then 0.408 gram of ammonia occupy 0.5376 liter, right? This is the correct answers. So this question is also very important, right? We have to solve this on the basis of mole concept as well as the related normality concept, that is number of gram equivalent. Number of gram equivalent of ammonia is equal to number of gram equivalent of sulfuric acid, right? In final case, which of the following cannot give the iodometric titrations? We have already discussed about the basic concept of iodometric titrations. In case of iodometric titrations, the different ions should convert the iodide ion into I2, means the oxidations of I minus to I2 should be taken place by these different type of the ions, right? So these ions should oxidize I minus to I2. So this should be in higher oxidation number so that they can oxidize the I minus to I2. So in above different options, Fe3 plus is in highest oxidation state, Cu2 plus is also in highest oxidation state. However, Pb2 plus is not in highest oxidation state. The highest oxidation state of lead is 4, right? Plus 4. However, in the options, lead is in plus 2 oxidation state, so answer will be C. So lead 2 plus, that is Pb2 plus, cannot give the iodometric titration because it is not in the highest oxidation state of lead. Highest oxidation state of lead will be 4 and silver is in highest oxidation state. So to give the iodometric titration, the metal ion should be in the highest oxidation state, possible highest oxidation state. This is important. Phenolphthalein is not a good indicator for titrating, right? NaOH against oxalic acid, NaOH is strong base and oxalic acid is weak acid. So strong base versus weak acid, the salt will be basic, and in case of basic salt, phenolphthalein could be easily used. Ferrous sulfate against KMnO4. This is an example of the redox titration. So in redox titration, we do not use any type of indicator in case of KMnO4 because KMnO4 itself is a self indicator, right? Itself is a self indicator. NaOH against HCl, it is a strong acid and strong base and strong acid. So in case of strong acid and strong base, we could easily use the phenolphthalein. This is also the strong acid and strong base we could use. So in case of B, we could not use the phenolphthalein as the indicators. It is an important example of redox titration. Acidified K-MnO4 solution is decolorized by bleaching powder, white vitriol, Mohr salt, microcosmic salt. Answer is Mohr salt. Here is the general equations of the above problems. Right? This Mohr salt decolorize the pink color of KMnO4 into colorless. Right? So KMnO4 has pink color and MnSO4 has no any colors. So it is done by Mohr salt. Mohr salt is dissolved in dilute H2SO4 instead of H2O to prevent the cationic hydrolysis. If Mohr salt is dissolved in water, then it performs the cationic hydrolysis with water. So it performs the cationic hydrolysis with water. So to prevent this, Mohr salt is kept in dilute H2SO4 during this titration. This is also an important example of redox titration. In the reaction, this reaction is based upon the iodometric titration, right? This is an important example of iodometric titration. Thiosulfate ion changes to tetrathionate and iodine changes to iodide ion, right? We have to calculate the equivalent weight of iodine, right? So the equivalent weight of any oxidizing or reducing agent is equal to molecular weight by total number of electrons either gained or either lost. So in case of iodine is changed from 0 to -1, means it is going to be reduced here. So it should get some electrons. So molecular weight of iodine divided by total number of electrons gained. How many number of atom of iodine is present here? 2. So what is the change in oxidation of single iodine atom? 0 minus 1. 0 minus minus 1 means only 1. For the 2 iodine atom, 2 minus 0. This means 2. So total number of electrons gained will be 2. So we have to calculate the total change in oxidation numbers, right? In case of single iodine atom, total change in oxidation number is 1. For 2 iodine atom, 2. So answer will be B, molecular weight by 2. However, in iodometric titration, equivalent weight of any substance belongs to that weight of that substance which combines with the 127 gram of the iodine, and 127 is the atomic weight of iodine, right? Atomic weight of iodine. The equivalent weight of any substance in iodometric titration is that weight which combines with 127 gram of iodine. So in case of the equivalent weight of hypo solution, right, Na2H2O3 here, if we put Na here, then Na2H2O3 plus I2 gives Na2S4O6 plus 2NaI. So that in such cases we have to find out the equivalent weight of hypo solution, and the equivalent weight of hypo solution is equal to the atomic weight of iodine. Means equivalent weight of hypo solution is that weight which combines with the atomic weight of iodine. So that is equal to molecular weight of hypo solution. So molecular weight of hypo solution is the equivalent weight of hypo solution. So molecular weight is equal to equivalent weight in case of the iodometric titrations for the hypo solution. So if the question is asked about the calculation of equivalent weight of hypo solution, then it is equal to the molecular weight of hypo solution. But if the question is asked about the calculation of the equivalent weight of iodine, then answer will be molecular weight of iodine divided by 2, right? Remember, these 2 points are very important. So this is according to the concept of this statement. So in iodometric titrations, the equivalent weight of any substance belongs to that weight which combines with 127. So according to these equations, what is the total molecular weight of iodine here? 2 into 127, because 127 is the atomic weight. Here are 2 atoms. So 2 into 127 combines with 2 into molecular weight. Then 127 combines with molecular weight. So this molecular weight will be the equivalent weight of that hypo solutions. Very important. Next question, 1 gram of magnesium having atomic weight 24 is added to aluminum chloride solution, atomic weight 27, right? This 27 is the atomic weight of aluminum, right? The amount of aluminum precipitated is. This question should be solved on the basis of this formula, that is weight is directly proportional to the equivalent weight, right? Weight of Mg divided by equivalent weight of Mg is equal to weight of aluminum precipitated divided by equivalent weight of aluminum. What is the equivalent weight of aluminum? 27 by 3. 3 is the valency of aluminum. So atomic weight by valency gives the equivalent weight. then answer will be 0.75 gram. Very simple question. 3.92 gram of ferrous ammonium sulfate reacts completely with 50 ml of n by 10 kmn of a solution. Then we have to calculate the percentage purity of the sample, right? What is the percentage purity of the ferrous ammonium sulfate, right? Percentage purity is calculated by calculating the amount of ferrous ammonium sulfate in pure form, right? Pure form means such amount of ferrous ammonium sulfate which combines with 50 ml of n by 10 kml of a solution. Among 3.92 gram of ferrous ammonium sulfate, all 3.92 will not combine with the n by 10 kMnO. Only pure form of ferrous ammonium sulfate combines with the n by 10 kMnO. So we have to calculate the weight of ferrous ammonium sulfate combined with KMnO by using the formula NEB by 1000. What is the normality of KMnO? That is 0.1. And what is the equivalent weight of ferrous ammonium sulfate? That is 392. We have already discussed about the formula of ferrous ammonium sulfate and calculation of the molecular weight, calculation of the equivalent weight. The equivalent weight of ferrous ammonium sulfate is equal to the molecular weight in case of redox titrations. This is an important example of redox titration. Then 50 is the volume of the KMnO solutions, right? This concept is also according to the number of gram equivalent of KMnO is equal to number of gram equivalent of ferrous ammonium sulfate. Whatever may be, answer will be 1.96 gram. So percentage purity is equal to 1.96 divided by total amount 3.92 into 100%. Answer will be 50%. Simple questions. Just use the number of gram equivalent of KMnO is equal to number of gram equivalent of ferrous ammonium sulfate. Next questions. If the weight of the metal and chlorine in a metal chloride is in the ratio of 1:2, right? This is the weight of metal and chlorine in metal chloride. The equivalent weight of the metal. We have to find out the equivalent weight of the metal, right? In case of metallic chloride, the equivalent weight of metal is that weight which combines with the 35.5 parts by weight of chlorine, right? According to the question, 2 parts by weight of chlorine, right, reacts with 1 part by weight of metal, right? 2 parts by weight of chlorine, because the ratio of the weight of metal in chlorine is 1:2. Then 2 parts by weight of chlorine reacts with 1 part by weight of metal. Then 35 part by weight of chlorine reacts with 70.75 parts by weight of metal. This 17.75 is the equivalent weight of the metal. So equivalent weight of the metal is that weight which combines with the 35.5 parts by weight of chlorine. Answer B. The maximum amount of barium sulfate precipitated on mixing BaCl2 having 0.5 molar concentration with sulfuric acid having 1 molar concentration will correspond to. So we have to calculate the maximum amount of barium sulfate formed. So this is the equations. Here is barium sulfate which will be precipitated out, and the concentration of barium chloride is 0.5 molar and the concentration of sulfuric acid is 1 molar. Then what is the maximum amount of barium sulfate formed? It depends upon the source type of the reactant which has lower concentration than the other. So what is the lower concentration among BaCl2 and H2SO4? That is 0.5 molar concentration is of barium chloride. So 0.5 molar concentration is of barium chloride, which is the limiting reactant, right? Which is the limiting reactant. So the amount of barium sulfate formed mainly depend upon the amount of barium chloride, as it is the lower concentrations, as it is the in lower concentration. The concentration of barium chloride is lower than that of the sulfuric acids. So the amount of barium sulfate formed will depend only on the concentration of barium chloride. So answer will be 0.5 molar. So how much amount of barium chloride is here? 0.5 molar. Then the barium sulfate will also be 0.5 molar. Right? And in this way, this chapter has been finished now, right? We have solved so many multiple choice questions related to the volumetric analysis, normality, molarity, molality, half neutralization, neutralizations, redox titrations, right? We have solved so many questions about these topics. We have also solved the entrance examination question which were previously asked. Similarly, we have also solved some of the multiple choice questions from the Indian entrance examination book. And this chapter has been finished now, and we will start another chapters, another lectures. Thank you so much.